Hello, hello. So, hi everyone. Good morning to all of you. How are you all? कैसे हैं आप सभी लोग? Let me check if I'm audible. Let me check if I'm audible. Very much. Anyways, so guys, welcome to this very amazing sessions by your one and only Sanjay Arya sir. And in today's session, we'll continue our organic chemistry as we are right now preparing for JEE 2025. A few of your chapters are left right now, and mostly from organic chemistry. So we have alcohol, phenol, ether in the continuity of GOC, hydrocarbon, haloalkane, haloarine. Now we have alcohol, phenol, and ether. So let me just give you the flow of this chapter. How are we gonna to go, by the way? So we'll do introduction and the classification part. Then we will cover the preparation methods. Exactly similarly what we have followed until for all the other organic chapters. We do introductory part, we prepare them, we know the physical and chemical reactions, and then we have important tests of alcohol, phenol, and over 100 plus PYQs plus practice problems we'll solve in this particular session along with PYQ. So let us start the chapter. Those who don't know me, guys, my name is Sanjay Arya. I have completed my graduation from IIT SM Dhanbad exactly 2010. I joined my college by that time, and from that time onwards I have been teaching the same for all the students of JEE Mains and Advanced and even NEET. So I have produced some of the good ranks, and my target is to produce even more. So guys, stay focused, stay tuned over here and give me the best result possible. This over here is the very first topic from this chapter, alcohol, phenol, ether, called as, what do we call it? Yeah, so we call it introduction and classification. We all know what is alcohol. Alcohol is actually whenever an alkyl or aryl part and one of the hydrogen is replaced by OH group, one or more, then it becomes an alcohol. Take this example, alkane. Alkane, when hydrogen is removed, OH group is added, it becomes alcohol. Similarly, if benzene is there, one of the hydrogen is removed and OH group is attached there, it becomes phenol. So that is the difference between alcohol and phenol, that alcohol is ROH, phenol is actually PHOH, phenyl group is here. One of the very easy question from here, general formula for alcohol will be, so guys, we all know that CN H2N plus 1 plus OH group. So guys, this is the formula. This represents simple radical of alkane, and this radical plus this is your alcohol group. So you can write it like CN H2N plus 2O. This can also be the formula. So tell me the correct answer. I guess A should be the correct answer. Next is classification of alcohol. So alcohols are classified under various categories, like depending upon so many factors here. Number one is how many number of OH groups are there. So let us say ki if the number of so what I'm saying is, if the number of alcoholic group or OH group, hydroxy group is just 1, we call such alcohol as monohydric. If the number is 2, we call it polyhydric. Polyhydric can come under dihydric, trihydric, tetrahydric, polyhydric, like that. Some of the good examples have been given here. Ethanol, methanol, propanol, butanol, all comes under the category of monohydric. And if you add two type of two OH groups, depending upon their relative positions, like there is like 1,1 hydroxy is there or 1,1 alcoholic group is there on the same carbon atom, we call them geminal diol. Similarly, if there are like 1,2 position, we call them vicinal diol, and rest out of them we call them normal 1314 like that only. Here are some example: ethylene glycol, we have propylene glycol, and then very good example glycerol. Glycerol is a very essential compound which is used in saponification method, preparation of soaps. Hopefully this works, and it's not working, no idea why. Hmm. We have another classification here, everyone. Just go through the classification. Second is for monohydric alcohols, and especially the monohydric alcohol which are containing yeah, various. Anyways, we'll manage it. Yeah. Every time I come and something is missing. Yeah. Anyways, yeah. Hi, Saranya. Good morning. So, guys, give it a look, everyone, and just try it. And allow me a moment. Not able to find where am I supposed to connect this part. No problem. So guys, depending upon the compound, if contains an sp3 hybridized carbon atom with OH group, so there could be like primary, secondary, tertiary kind of thing can be there. Depending upon on which carbon it is attached with, this is 1 degree carbon, alcohol becomes primary. This is a second degree carbon atom to which OH group is attached. And since this carbon to which directly the OH group is attached is 3 degree, so we have primary, secondary and tertiary alcohols. Next classification is based upon the presence of double bond, presence of a sp2 hybridized carbon atom. So if a carbon atom is sp3 to which alcoholic group is attached, and the next to it carbon is sp2, we come under allylic category. We call them allylic. Now this allylic can also be 1 degree, 2 degree and 3 degree depending upon the directly bonded carbon to which group is attached to how many other carbon atoms. Take an example. This carbon atom itself, which is directly attached with OH, is attached with 2 carbon atom, and the next one, this one is sp3 and this one is sp2. This comes under the category of allylic, but this is secondary allylic. Similarly, we have tertiary allylic. Take an idea, guys. Note it down. We have benzylic alcohols with us. Benzyl group is what? Carbon atom directly bonded to a benzene ring. So definitely this is also a type of allylic system where you have an sp3 hybridized carbon which is directly connected to sp2. This is sp2 and OH group is directly connected with sp3. Allylic kind of system is there. This can also become 1 degree benzylic, 2 degree benzylic, 3 degree benzylic, depending upon that the OH group is attached to which degree of carbon atoms. This is 3 degree, 1, 2, 3, attached with 3 other carbon atom. This is simple classification, guys. This is simple classification. Next we have compounds containing directly attachment with the OH group, which is the carbon is like sp2 hybridized. So we have this kind of system called as a vinylic system. There's a difference between allylic and vinylic. In allylic, we have a carbon atom which is sp3 hybridized, which is directly connected to OH group, and then this carbon is attached to a sp2 hybridized carbon. Over here, OH group will be directly attached to the sp2 hybridized carbon. We call such alcohols as vinylic alcohols. So sp2 hybridized. And similarly, guys, this is called as phenolic group, but again, it is also a kind of vinyl system. We can see vinyl, OH is connected to carbon, double bond carbon. It has a common name. We call it phenol. 2-methyl phenol can also be called, and orthocresol is its common name, which again has been accepted as an IUPAC name only. We have a set of some examples for which we directly use their common names only instead of writing their IUPAC. So this compound belongs to that. Name is orthocresol. Ortho is the relative positions of these two groups, direct adjacent to this 1-2 positions. So anyways, I'm still figuring out. Chalo. Then we have one question here. Glycerol. Formula of glycerol is CH2OH. We have CHOH and CH2OH. So guys, it's a what? Trihydric, because 3 alcoholic group are there. We can simply like trihydric alcohol, depending upon the number of alcoholic groups. Another question, the common name, we have common nomenclature here, everyone. Will not take too much of time because we already have spent so much time on this earlier in our GOC lectures. Anyways, I'll give you the idea how to write common name and then how do you write the IUPAC. IUPAC, you people are very much comfortable in, and talking about the common name, we'll understand over here. One more thing I want to add is my notes are very much self-explanatory. So those whoever are watching my video, guys, you can download the notes from the link given in the description. You can go to our Telegram channel where you can find the link related to the notes. After finding the notes, you can start preparing your own notes. Those who are preparing for JEE 2025, my suggestion is to make the short notes out of it, and so that short notes can help you to like quickly recover, quickly basically learn the whole concept of this chapter, like within some good set of time. And those who are preparing for 11th and especially right now in 12th, or might be planning for upcoming like 2026 program, then they can make full notes out of it. That is their choice. But these notes are self-explanatory. Enough of the problems as a practice I have given. Enough of the content we have up to JEE Advanced. So guys, just do one thing. Just quickly revise the whole lecture once after you have completed my lecture, attending over here, and then write, making the short notes out of it of 1 or 2 page containing all the chemical important reactions and the mind map, like how am I proceeding. That was a suggestion to all JEE 25 people. Now let's come back to our topic. Common name. Common name is alcohol, like ethyl alcohol, methyl alcohol, propyl alcohol, butyl alcohol, like that. And in common name also we have isopropyl alcohol. So that's how we name it. So take this idea, everyone. Let us say this is an alcohol. Metheth prop. We call it N-propyl alcohol. We call it isopropyl alcohol. This is common name. So what about its IUPAC name? So the IUPAC name will become what? Alkane-ol, propane 1-ol, and this will become propane 2-ol. Right, everyone? So this is IUPAC versus common naming. And in both of the cases, we use alcohol versus ol. Let us have one question here. We have one question here, everyone. So this is propane 1 through 3 triol. It's common. It's IUPAC name actually, and we know that where to put the di, tri, and tetra, like that. So I'll give you one example, directly this example. Whenever we are naming a particular given organic compound, what we have to take in our mind that functional groups is principal functional groups specifically are given the most priority, followed by multiple bonds and followed by substituent. So what we have to do is give it the least number possible. So 1, 2, 3, and from here it is 1, 2, 3, and 4. I guess 3 is better. Then we will go 5, 6, and 7. Not just 4, 5, 6. We have an alkene also. We have 6 members. There is no substituent, so we'll simply write hex. Then where is the ene? I have hex 1 ene 3 ol. So that is how we name hex 1 ene 3 ol. See, and hexene 3 ol or can also be said for this compound hex ene 3 ol. That's very easy of this topic, IUPAC naming. We already have covered this part. That's why we'll go a bit fast. We'll solve some questions. We have a substituent over here as Cl, but we all know that priority must be given to the functional group only, and functional group is alcohol here. So 1, 2, 3, 4, 5, 6. The longest chain which can include all the substituent and all the functional groups and all the multiple bonds will be this chain. We have 5-chloro here, 5-chloro, hexane 2-ol. I guess C is the correct answer. Okay, I would expect you people to participate in these kind of quizzes and practice part so that you can also become comfortable in solving the problems, which is a important part of this session. We have a question here, everyone. Glycerine, propane 1, 2, 3 triol has what? 1 primary, 2 secondary, as we all know. So this was the structure CH2OH, CHOH, and then CH2OH. Now you can find it. What is the degree of carbon atom over here? This one is connected to one more, it is 1 degree. This one is connected to two-sided, it is 2 degree. This is also 1 degree. So we have 2 primary and 1 secondary. Where can we find 2 primary and 1 secondary? 2 primary, 1 secondary. I think B option is correct. See how easy? How easily we have done this question. We have another question, the structure of cyclohexanol. So cyclohexanol will be what? Cyclohexene. So one ene will be there, and exactly on the same position it should be there. Oh, I thought I have done it correctly. No, it's just cyclohexanol, not a double bond, not hexenol. It's just hexanol. I guess A should be the correct answer. Very easy question. Very easy one. Give the correct IUPAC name. I can give the name very easily, like 1, 2, 3, 4, 5, and 6. So it will be hexane 2. C is the correct answer. Now we have come to preparations of alcohol. Till now, whatever we have learned, that was a basic introductory part of alcohols. A very few questions have been asked from this part. Now, majority of the questions in our examination either comes from the preparatory part or it comes from the chemical reaction part. So let us start focusing on the preparation of alcohol. We have plenty of methods here, because till now we have covered hydrocarbons, we have covered alkyl halide, aryl halide chapter. So we all know that in those kind of chapter, whenever we were up to what I must call it, preparations or up to the chemical properties of these compounds, somewhere we found that alcohols were formed. Now those reactions will be used here as a preparation methods of alcohol. Let us bring the first chemical reaction from alkanes. Alkanes usually don't react. Alkane, their names like they also are called paraffins. Para stands for less reactive and fin is the activity. So paraffins are actually very less reactive hydrocarbons, and only 3 degree hydrogen containing alcohol can be oxidized using a strong oxidizing agent called as KMnO4 and converted into alcohol. So this reaction can be shown up to, this is tertiary butanol, not tertiary butanol, this is tertiary butane, or not butane, method prop. We also can call it isobutane. And then in the presence of this strong oxidizing agent, we have converted into OH. Other secondary and primary alkanes do not give this reaction, only tertiary. So always remember, only this reaction is only for 3 degree hydrogen. We have next from alkenes. So we have to prepare alcohols from alkene, and there are several methods, and out of which some of the methods are pretty important, and I must give all of these reaction at once somewhere, probably here. And as you all remember, I have taught you this part very very earlier in hydrocarbon chapter. Now take this example, everyone. So let us suppose we have been given with an alkene. So if this alkene, so alkene is undergoing what? Addition of HOH. We call this process as hydration of alkene. So guys, hydration can occur under three possibilities. The number one is called as acid catalyzed. We follow an acid catalyzed mechanism here, and the reagent we use is simply dilute H2SO4 somewhere, or any acid you can take, or H3O plus might be there, H plus might be there. This is all representing alkene. Always remember, the product over here will be, the product from this reaction will come up as Markovnikov product with rearrangement of carbocation. So if there is a possibility of rearrangement, then it may undergo rearrangement of carbocation. Correct? First part. Let us suppose we have second round with us. So guys, second round is actually called as oxymercuration, demercuration, OMDM. Reagent we use, number one is HgSO4 first, followed by, first we use HgSO4 in order to prepare a, not HgSO4, mercuric acetate sometime we use, HgOAc whole twice, and then we use demercuration. So NaBH4 as a reducing agent. So this is the reaction. HgOAc NaBH4. We have oxymercuration, demercuration. Here, always remember, what we have to do is, we are maintaining that Markovnikov product will be the major product. This will give you the Markovnikov product. And we are not supposed to do any rearrangement, so no rearrangement of carbocation, which is even simpler now. We have third possibility, and third is actually called as, third process is called as hydroboration oxidation. So we are first now adding boron hydride, reducing it, and then later on we'll oxidize it. So remember the reagent what we are using over here. We have initially B2S6 THF, which is called as diboron attached with tetrahydrofuran, which holds this compound or this molecule, and then we have to use oxidizing agent. Let us take out H2O2 here. So remember that this comes first, this comes second. So here it's very easy that we can directly identify the product. So we will make anti-Markovnikov addition will be taking place, and also there is no possibility because there is no carbocation formed in this method, so no rearrangement. No rearrangement of carbocation. Even no carbocation is formed. And the same with here. This is how we do. So this is actually the overall analysis what we have done for all three type of reactions. Possibly the hydrolysis of alkene, which we are following with the hydration and attacking H2O directly on the carbon double bond carbon alkene part. So let me take you to one example from here, everyone. Let me take you to one example, one very pretty example. We already have covered such examples earlier. So let us suppose this is a benzene molecule, and the benzene is attached here with some alkyl chain part. This is the best example actually. So guys, let us suppose first reaction which we are doing is we are using dilute H2SO4. So simply the product should be one, first of all, H plus will be attack here. H plus will attack on most, where most stable carbocation will be formed. This is 2-degree carbocation. Here it will be formed. Go for 1,2 hydride shift so that it can become more stable. The final product will be a rearranged product and will look like benzene. We have CH, and here directly this group is connected, CH. This is already having OH group over here, and then CH double bond, CH, not double bond here. CH2, CH3. Hopefully, yeah, it's equal. So if we are bringing the same reaction in the presence of number one, we are using oxymercuration, HgOAc, whole twice, then an attack of reducing agent NaBH4. So this compound will give you direct Markovnikov's product rather than any rearrangement. So this will look like exactly the same, only this carbon atom will be connected to OH group followed by one CH3. We have third oxymercuration, demercuration. Right after that we have hydroboration. So BH3, THF. Then we have oxidizing agent H2O2, OH minus. So this will produce anti-Markovnikov. So this will become like CH2. We have CH2 and we have CH2OH. That's how it look like. So check it out, everyone. So here I have taken all the possible cases and I have cleared all your related doubts that from alkene this kind of reactions may take place. This kind of product can be formed. We have a question here. We have a question. The question says that one of the alcohol which exactly look like this. No, it's an alkene. So this is what I can see. It's anti-Markovnikov's addition. So let me just write it. This is anti-Markovnikov. This is simply Markovnikov's, no rearrangement. So this is like what? OMDM, and this will become what? HBO, hydroboration oxidation, and this is oxymercuration demercuration. So what I have to give is second and first are. So second one is hydroboration oxidation and the first one is oxymercuration demercuration. So read the statement correctly and then pick the answer. I guess B should be the correct answer. Very clear to all of you. We have another chemical reaction, and I hope all of us have already completed this part. It's a cyclic, pericyclic, single concerted cyclic mechanism where the molecule itself rearranges itself, giving you the final product, which is an alcohol. So vicinal diols are formed using this reaction, where Bayer's test, we also give it a name of Bayer's test. Alkene when react with the dilute alkaline KMnO4, and it is cold dilute KMnO4, which is also called as Bayer's reagent and Bayer's test. Syn addition of OH group takes place. The similar formulation takes place in the case of osmium tetraoxide OSO4, and the same reaction will take place. Syn addition of OH group takes place. I don't need to remind you the mechanism, which I have already explained you in the hydrocarbon part. The mechanism is absolutely not important. Just need to know what molecule are we given with. Attacking reagent is what, and what is the product. That is what we have to learn. Wherever it is required, I'll give you the mechanism. However, the mechanism given, I am again explaining you, no requirement of rote learning down this mechanism. It's very simple, just taking you the idea that this is a syn addition. We have similar reaction with OSO4. The third reaction is actually using the peroxy acid. So guys, peroxy acids, do you know what is the purpose of a peroxy acid? A peroxy acid or a per acid attacks upon alkene and gives you an insertion mechanism introducing a cyclic ether. The cyclic ether, when it is attacked by an acidic or basic medium by an OH group or with water, it produces you an alcohol. So that's how it is given to you. So where we have a list of some important peroxy acids, they are like peracetic acid. This is not supposed to be learned by you. Just take the idea and just get comfortable with it. We have CH3COO. So it's not COOH will be there, because acidic acid will be having OH. Per acid is having this OO bond, which is called as the peroxy bond. Peroxy bond. We have metachloroperoxy benzoic acid, which is another very important reagent that we'll use in preparations of ethers. Check out the mechanism, everyone. So again, I told you that no need to go through this very detailed mechanism of this. Always remember this: a doubly bonded carbon and an alkene on attack with per acid. So whenever a per acid attacks, it gives you a epoxy, which is called as cyclic ether. This cyclic ether, when comes under the contact with either water or it is like in basic medium, I'll explain this mechanism a bit late when we will be dealing with ethers preparation. The chemical reactions of ether will explain this part, like where we have to consider the attack upon most crowded carbon and where we have to supposed to attack with least crowded carbon. These reactions are SN1 type and SN2 type respectively, depending upon the medium which we are using. In generally acidic medium, it is SN1 type reaction. In basic medium, or if the attacking reagent is a nucleophile or OH minus group, in that way we consider this as SN2 type reaction. So we'll explain it later on. Now let us move ahead. Let me give you this idea, guys. So metachloroperbenzoic acid, no need to write down any mechanism. We already know that it gives you a simple insertion mechanism, preparation of cyclic epoxy. Then reagent used for the syn dihydroxylation. Alkaline K1O4 is fine, because this will prepare what? This will give you cyclic ether, and this is called as Bayer's test. Bayer's test gives you vicinadiols. We have a question here. In the following reaction, give us the all products and find out the major product. So anyways, what exactly happens here? We have a first product, not a first product, it's a reaction intermediate. So this intermediate look like this, because the very first attack takes place of H positive, and this double bond attacks on H positive in such a way that one of the carbon is acquiring positive, another one is acquiring negative. The negative one will accept H positive, and this is like H positive, it has been taken by negative charge. This no doubt will become a carbocation, which is now a 2-degree carbocation, which wants to get stabilized. In the next step, 1,2 methyl shift takes place. So from here, a methyl group with its electron density attacks here, so that a positive charge will be created over here. We will be getting a rearranged product like this, with a positive charge on this carbon atom. The another will be connected by 1 CH3, and 1 CH3 was already here. So what is the benefit of this carbocation we have? This is a tertiary carbocation, relatively more stable. In the next step, we will be getting the attack of water and then removal of H positive, as this reaction is acid catalyzed. Initially H plus will be added, at last H plus will be removed out. So how it is made? So we have CH3, OH, CH. So this is our major product. So what if we have to make the minor products also? The minor product may come from here. Darkly OH can be attached here. But we know that most stable carbocation will give you the major product, so this will give you the major product. We have a question. The final product of the reaction will be. I think we all have completed this part, already covered. So you need to do the homework by your own. This is something which is already covered. So wherever I'll find something is repeated, I will either ask you to do the homework or I'll write it already covered. Alkene can be converted into alcohol by which of the following reaction? Or no doubt it is elimination. Alkene can be, no, it is addition reaction. So the reverse of this reaction will be a elimination reaction. So check it out, everyone, check it out. Let us suppose this is an alkene and we are just adding H plus and OH minus. So this is called as electrophilic addition reaction, and the product will be somewhere H will be attached, somewhere OH will be attached. Now the question is, this process is actually what? Addition reaction. And if you go backward, it will become an elimination reaction. Try this question. Good morning, everyone. I might not be entertaining you guys, but don't worry. I already have known across your all the comments. And why am I not replying right now? Because I have a very huge chapter with us, which will definitely gonna to take 4 to 5 hours. So that's why I just want all of you to stay focused. And whenever any kind of doubt come, do let me know. I'm continuously reading all the chats. But wherever you are just simply wishing me greetings, I already have said very good morning to all of you. It's not so great morning, waking up very early, coming to the office even on Sundays, but anyways it's manageable and enjoyable also. We have a question: which of the following alkene will give you the same product by hydration, by HBO and oxymercution demercuration? So this will happen in the case of, in symmetric alkene it may happen. Symmetric alkene, which is having no difference in the groups attached to the doubly bonded carbon, symmetric alkenes only this can happen. Now try to find out the symmetric alkene. Symmetric alkene is here. B is the correct answer, because you can identify either by checking that doubly bonded carbon has similar group, methyl, or you can give it a IUPAC name by going left to right and right to left. You will be getting the same name. That's an identification of a symmetric alkene. We have another such question with us. We have a KMnO4, then we have water and OH minus. Now what do you think? What is going to happen? Anyways, this is some very easy question, and we already have came across this test called as Bayer's test. So the product will be a vicinal diol with a similar syn addition. So let's say this is OH and this will also be OH, right? So I think this is X. B is correct. Then we have meta chloroperbenzoic acid, and we all know per acid does what? Makes a this kind of compound, which when attacked by water, this leaves out like this, and in acidic medium this will become what? So this both, this is Y. So I think D is the perfect answer, explaining both X and Y. So attack on ether by water, it's actually taking you more or less like anti-addition. Why am I calling it anti? Because water which is attacking is and the leaving group, they all belong to different sides. Okay, that question was appeared in JEE Main 2019. Yeah, how easy question was this? People who appeared the JEE 2019 exam, they are feeling very lucky now. How easily they finished this question. Now we will move forward. We have another important compound called as alkyl halide to prepare alcohols. So one of the common reaction is called as SN1, SN2, any nucleophilic substitution reaction, and the another one could be by attacking of Grignard reagent on a carbonyl compounds actually. So let us take example of this. So guys, RX on attack with water can follow SN1 reaction, where you can get ROH, or ROH this could be 3 degree and then 2 degree, and primary do not give this reaction. And similarly, if you are attacking with NaOH, where an OH minus is a strong nucleophile, it will go for SN2, and then 1 degree and then 2 degree, 3 degree will not give this reaction, and this will look out for the ROH. We have already covered this part in our previous chapter named as alkyl halide, aryl halide, and now we have some set of reactions with us. So guys, first of all, let me give you this idea that let us suppose we have RMGX, and a very simple RMGX could be, first of all, let us take this HC double bond OH. What we call this compound as formaldehyde. So formaldehyde on reaction with CH3MgBr, no doubt this reaction occurs in dry ether, and then we are following, so I must write it like this. So first we are attacking with CH3MgBr, preparing a magnesium compound only. Second, we are hydrolyzing it, H3O plus. Then it will give you HC. Then this will become OH. Initially it was OMGX, but then it becomes, after hydrolysis, O like this. And CH3 has been attacked there. So CH3, and here is H. So guys, what you are getting is a 1 degree alcohol, primary alcohol. So primary alcohol will be achieved using formaldehyde only. No other options are there. We have CH3C double bond OH. We call it as acetaldehyde. Acetaldehyde on reaction with the same compounds will give you CH3, CH3, H and then OH. So guys, this is a secondary alcohol. So let's say you can take any of the ketone. This is called as acetone, but any of the ketone can be taken. And the ketone with the similar reagent will produce you. See, we have CH3 group in all three directions, and it's a tertiary alcohol we got. It's a 3 degree alcohol as a result we are getting. So just simply have a look on this. And then in my next lecture, probably I'll come up with just Grignard reagent, explaining you the all detail of Grignard reagent, how is it formed, what chemical reaction does a Grignard reagent do. So we'll explain you that part. Right now we'll cover alcohol phenol ether, and then we'll give you the idea. We have acid derivatives which can be represented like this. So this is a acid derivative now. G could be a leaving group, and these reactions are called SN2 type, SN2TH reactions. We call them reaction like SN2 bimolecular nucleophilic substitution through tetrahedral intermediate. So the attacking reagent will be no doubt R-MgX with a negative charge on R minus, attacks here like this. This minus charge can go there, removing this. I'm writing in a single step only. Let us check the final product. R C double bond O. Now G group has been removed by R dash. So actually what we are getting is a ketone. So now you need to get this compound reacted with another equivalent of R-MgX, and then only you will be getting the product. An alcohol which is looking like tertiary. But depending upon what R group is there, it could mean hydrogen also. We will get our product. You face any doubt, you need any like help, please comment me in the comment section. I'll help you. I'm still unable to find this. It's a pen drive looking like thing, and I don't know where is someone put it, and I'm not able to find it. Then addition to alkane nitriles is one of the way, and this nitrile addition can also takes place in multiple ways. If you want me to explain it, I'll give you a simplest way. Let us suppose we have CH3C triple bond N. It is called as ethane nitrile. So ethane nitrile on reaction with, let's say, CH3 MgBr, and this reaction takes place in dry ether only, because this is a strong base and this is a strong nucleophile. In presence of water, it can acquire the acidic hydrogen, and acid base reaction will take place, forming alkanes as a product, and that is what not a desired product of ours. So I will first lead you to the intermediate form. So intermediate looks like this: CH3 C. So one of the CH3 will attack here, a double bond is here, and NH. Actually NMgBr will be there, but let's say one hydrolysis we are doing, or you can mention this rest of the compound also with NMgX. Right after that, if you go for the hydrolysis, it will take you two equivalents to hydrolyze this part. It's a double bond there. So we will find C will be attached with OH with CH3 plus this N, which was already connected to Mg. MgX will be now connected to H and H. So this is how it look like, and we know that this is unstable. It will be removed out, it will eliminate out a water molecule and will form a compound like this. So more or less acetone is our product here. Now again, one more equivalent can lead to formation of tertiary, because ketone on hydrolysis, or like ketones upon attack of RMGX followed by hydrolysis, gives you tertiary alkane. We have another reaction here, and that is addition of cyclic ether epoxy, and we already have covered this part everyone, so I'll explain it to you later on, not right now exactly. And we right now are completing the reactions or preparation through Grignard reagent, so we'll cover it later. Let me just write you, we will cover it later. We'll cover in ethers, chemical reactions of ethers, will cover it, so don't worry, it will come. And let me just brief you right now about it, that if any cyclic ether is there. So guys, let us suppose this is how it look like. So guys, this is how it works. Let us suppose you are attacking it with water or in acidic medium, then the product will be like this. More hindered carbon atom will acquire the attack of OH. Let's say this is O18, H218. This is how it look like. But if the same reaction is carried out using basic medium RMGX, and this reaction is SN1, not SN1, this is SN1 type, this is SN2 type. So RMGX, R minus MGX plus, so this will give you O minus MGX plus will be the here. No, not like that. Here it will take the place, the attack will take place from here. So this is R, or let's say this is R, this is your OMGX, and here are two groups like this. This is SN2 type, this is SN type. So we'll explain it later, where in the chemical reactions of ether I'll explain it. The complete mechanism will be explained by me, so don't worry. Just take the idea and let's move forward. When alkyl halide react with aqueous KOH, alcohol will be formed, no doubt, very easy reaction, because we are using aqueous. If it is alcoholic KOH is stronger base than a stronger nucleophile, and then it will produce alkene. Which of the following combination is suitable for the preparation of 3-methyl 2-butanol? So just write question and allow me a moment, everyone. This reaction or this question was asked in JEE Main previous exam, and I'll bring this remote. Allow me a moment, and you people keep on trying this question. I'll be back and joining you in 2 minutes, a couple of minutes. So guys, I could not find the one I was looking for, but fortunately got some good coffee. It's Sunday today and I can't even ask someone for the help. You all must be observing that I'm facing difficulties right now in order to switch the slides. And the remote is not working. And it's not about the remote, it's about the kind of a drive which is fitted here, and I don't know where is it exactly. Okay, we had this question which was asked somewhere as in JEE Main. Now it seems like my pen is missing. Let me try this question. 2-butanone methyl magnesium bromide. No, will not give 2-butanone. And the reaction with methyl MEMGBr. So this Me group will go here and attack, followed by hydrolysis will give you this compound. So what is this compound? This is actually 2-methyl 2-butanol. So we need to get the 3-methyl butanol. I think this will be fine. C, because this isopropyl group will definitely be having a methyl group somewhere else. Try this. Acetaldehyde is this. And then we have isopropyl, IPR, MgBr, 1 followed by hydrolysis, no doubt. So we'll give you a product like this. See, CH3. Then we have one OH here, and now let us say CH. This will be connected to IPR group. So this is CH, CH3, CH3. So see, 1, 2, 3, 4. 2 alcohol and 3 methyl. So C is the perfect answer. So we need to have this common sense actually while solving these questions. And it's not a very special question, and we didn't require any special knowledge about it. We had the common sense, we got the idea that 2 or 3 positions is only possible in the case of isopropyl group. Ethylene oxide when treated with Grignard gives you what? Ethylene oxide. Okay, ethylene oxide. I didn't know about ethylene oxide. Actually, this is ethylene oxide. This is ethylene oxide. This will be HH only. So it's asking that on reaction with RMGX, let's say followed by hydrolysis we are doing. So this is OH and here is R, and opposite side attack takes place here. So this will lead you to the formation of a secondary alcohol, because this carbon, no, it's primary or what? Ethylene. So this is a carbon atom, and it is, since this is 1 degree, I find this is 1 degree. So that is why primary alcohol will be formed. Cycloalcohol will not be there. We have third from carbonyl compounds, which is another important reaction. Carbonyl compounds, either we can go for a reducing agent or we can directly get it attacked by the Grignard. Grignard we already have covered, now we'll reduce them. So these important reducing agents are these, learn them. These are the reducing agent which can convert an aldehyde oblique ketone into respective alcohols. So try learning it, and always remember that an aldehyde always gives you 1 degree alcohol on reduction, and an acetone always gives you secondary alcohol. So using this reaction, you can never form or you can never prepare a tertiary alcohol, but primary and secondary can be prepared by using this method. We have list of some reagent which can reduce down to what. Please have a look everyone and just note it down, take a snip and just write down all of these important reagent. Until then, I'll keep on searching what I was looking for in the beginning of the lecture. Hmm. Anyways, it's interesting. Sir, is this a PYQ? Which question are you talking about, bro? Bro. So where were we? So these are some set of reducing agent that we use, like LiLH4 can reduce aldehyde to primary, ketone to secondary. LiLH4 in excess of this can lead you to the formation of 1-degree alcohol directly, because the first reducing like reduction of an carboxylic acid will lead you to the formation of aldehyde, and then only it reaches to 1 degree. Then NaBH4 is something that can be used to reduce down only aldehyde and ketone, and not other carboxylic acid derivatives. And derivatives, okay, esters will not be reduced. So this is something that is very important for all of us to take an idea, that LiLH4 can reduce all the like carboxylic group, carbonyl groups, also the derivatives of carboxylic acids also, and even to carboxylic acid we can reduce. And the same thing can happen with H2Ni being a strong reducing agent, another strong reducing agent, but NaBH4 cannot reduce. It reduces selectively. Selectively, that means if you want to stop your reaction and there is an aldehyde group there, and there is a carboxylic acid group, and you need to only reduce down to aldehyde group to the alcohol, and you do not need to disturb the RCOH group like carboxylic acid group. So then you need to take NaBH4. This is more selective than LiLH4. Similarly, esters cannot be reduced. So we have a general mechanism here. Everyone please have a look, focus over here, and general mechanism is in like what actually happens there. So whatever the NaBH4 we are using, and that's hydrogen will be attached here, one of the hydrogen, and this O minus will attack on water, and OD will be the this is how we mention it. By talking about the LiLH4, similarly one hydrogen will be attached, the hydrogen is coming out of here, and then the so formed compound will attack on water, and this OH will be finding over here. No, not like that, only just a hydrogen. Only hydrogen, correct? This hydrogen. I'll take you directly to some of the good applications of this part. So NaBH4 will be able to hold acid derivative. This is false, and it doesn't reduce to carboxylic acid and the esters also. We have a question that carbonyl compound are reduced to alcohol by hydride reagent, correct? And the reduction involves addition of 2 hydrogen across this, correct? True. We have reduction of carbonyl group to alkoxide, which is protonated to alcohol, correct? True. We have both type above. Yes, C is the correct answer. So more or less the reaction takes place in such a way. A kind of nucleophilic addition reaction occurs for of hydride. This forms O minus, and a hydrogen is attached, and then followed by H plus, and this is how it is formed, alcohol. Since we are taking one shot, I'm drinking my coffee in one shot now. Single shot, coffee finish. Try this question, everyone. Try this question. We have a CH3Br. So this is SN2 reaction taking place. And CH3CN will be the product. If AgCN would have been used here, I told you in the previous lecture, then CH3NC will be the product. Iso nitrile will be the product. Isocyanide. Followed by this will give you what? CH3C. So CH first it will be attached to, and then C double bond O will be there. Along with nitrogen will form NH3 and will be eliminated out. This upon the reaction will give you OH, H and H. So I can write it CH2OH. So ethanol is the correct answer, I guess. Ethyl alcohol, ethanol, D. Let me see who has given me the correct answer. Shreyas is saying hello. Hi Shreyas. Guys, please try solving the questions because hi, hello will not come in your exam. These questions will come in your exam. We have very beautiful question looking like. We have this kind of compound with us, which is a cyclic ester. And cyclic ester is attacked by LiLH4. And we all know that in such compounds, this will be converted. Getting me? This will be converted into OH. This will be like broken down. This will also be converted into OH. This is like OH using LiLH4. But NaBH4 does it selectively, will not impact this part only to this part because esters will not be affected here. Only the aldehydic part will be converted back into alcohol. This is how it looks like. Now you see where is the correct answers. So A. So B and C we have to tell. B is this and C is this. So actually B is this, C is this. I think A is correct answer. A is the perfect answer here. So try solving by your own, everyone. Ninad is saying C. No, C will not be the correct answer, Ninad. Check it out. I told you selectively reduction will be done by NaBH4, which does not disturb to ester group. It only disturbs to the aldehydic and ketonic group. But LiLH4 can reduce all. Let's have another question that we have LiLH4. What will be the correct product out of it? So it's very easy. First of all, this part, aldehydic or ketonic part, will always be converted into OH. We have aldehyde here, which will be converted into CH2OH. We have this part, COH, and that's it. And it will be attached with OH2, CH2, and we also have CH3OH with us. So now you check what is the correct answer here. I guess this is the perfect answer. Yes, C. C is perfect answer in this question. Ninad. Then we have this question. I guess you must try this question by your own. I have plenty of things to cover. I'll move forward. We have now physical properties of alcohols. So in our first hour of this session, we have completed the preparations of alcohol. Now, since alcohols are prepared here, now it's time to utilize the alcohols. Kidding. We will learn the physical properties of alcohol from here. State lower members are actually liquids and higher one are the waxy solids. Lower one is methanol, ethanol, propanol. These are liquids. Higher one are actually waxy solids. They are colorless in nature and in appearance, and they have some faint odor. Glycerol is odorless, but they have some faint odor, some smell, characteristic smell of alcohol. Then solubility is good. Lower members are highly soluble because of the formation of H bonding and a smaller hydrophobic group of alkyl group, but higher members, because carbon chain is hydrophobic in nature, will become less and less soluble. Flammability is high. They basically produce smoky, non-smoky flame, blue colored flame. Somebody of you might have seen in the movies. It has been shown that somebody is taking a fire shot there. Vodka is being burnt there. The ethanol part is burning with a blue flame there without any smoke creation. We have boiling point here. Boiling point is higher than comparable molecular masses of the alkanes. So alkanes, and let us say Rx is there. Even beyond that, alcohols will have their boiling point because of the intermolecular H bonding. Boiling point is directly proportional to the molecular weight. As the molecular weight increases, their, we can say, van der Waals force of attraction increases, and so does their boiling point increases. And inversely proportional to the branching, because branching increases, surface area decreases. And you can check out that how it is increasing with the number of carbon atom, and it is decreasing with the branches. Take this idea and then I'll move forward. Then we have boiling points. Why are higher than ethers? Because in ether there is no H bonding. In water there can happen an H bonding because of ROH group. ROR, they don't do any H bonding, but only they are like polar molecules, and that's why they have some dipole-dipole interaction. But that is also a very small level of attraction, which causes ethers to be more volatile with less boiling point than comparing to alcohols. Moving forward, we have a question that boiling point of alcohol is more than corresponding ether. Is it true? Yeah, it is very much true. Because of this bonding. Which of the following alcohol has the highest boiling point? Methanol, ethanol, propanol, isopropanol. Only propanol will be the correct answer. Linear molecule with no branch. And this will be a non-linear molecule, linear molecule with a branch in this. So we have diethyl ether and ethanol have the same molecular weight, but ethanol has greater because of the hydrogen bonding in alcohols and no such thing in ether. Finally, we have come to the chemical reactions of alcohol, another important part of this chapter. So individually we'll cover all the segments of this chapter. We have right now with us alcohol. We'll come to later on with phenol and then with ether. Same strategy will follow. We will first create them, preparations, then we'll use their physical properties. We will ask their some of the uses at last, and then we'll do the chemical properties of these compounds, which is also called as the chemical reactions of the compound. So we have chemical reactions of alcohol. Let us see first chemical reaction of alcohol. There will be two type of reactions. So guys, this is how it look like. If this is breaking, then we have acidic reactions. So acidic nature of alcohol will be shown here. And let us suppose if you are breaking this bond, then in that way, what we can say is either it is making R. If H is removed, H positive, it will showing this, and if this is removed, then kind of like substitution reactions can occur here. So, and acidic nature will be shown. So let us first go for the type 1, where we are attacking on the R part, not on the hydrogen or not on the oxygen. We are attacking on the R part, carbon we are attacking with. So the very one reaction is number 1, dehydration of alcohol. Guys, this is something that we already have learned so many times in our previous chapters also. Like in hydrocarbon, we studied about the dehydration of alcohol forming alkenes. So it's an easy reaction. This usually follows even process, generally follows what? Even, but it can also follow E2 if the what I can say, the reagent over there, if what I must say, if 3 degrees is not given to us, and under that way we have to manipulate the reaction. But anyway, usually it follows even mechanism, and around H2SO4 and around 433 to 443 Kelvin on this temperature range, under heat, it gives you elimination product, alkene. So take this example, and I have already given you this, that secondary and tertiary can undergo under milder condition, as they can give a stable carbocation to you. But this, like, take this example, I'll explain this part, that concentrated H positive is here. So this H positive will attack here. Since the resultant carbocation will be a tertiary, water is automatically eliminated out. the reaction intermediate formed will be a tertiary carbocation. So later on, with the attack of water or HSO4 minus, one hydrogen will be eliminated out. This is how it look like. An alkene will be formed as a product. It follows as even mechanism. But if you talk about the primary one, so usually guys, primary can be dangerous. Primary alcohols usually do not go very easily, and they then follow E2 elimination reaction. How? I'll explain you. So hydration of alcohol follows three-step mechanism. One is the formation of protonated alcohol, carbocation, and then formation of the alkene. And elimination reaction covered in alkyne and aryl halide also in detail. It has been already covered, so I'm not taking too much of our time. Mechanism is mentioned. You can also go for the more stable carbocation, and always must know that more substituted alkene, more group containing alkene will be the major, and this is called as Sedzev product. And the lesser substituted alkene is called as Hofmann alkene. And since we have already covered this part in reaction mechanism, let us not waste our time and let us move forward then. Sedzev rule is pretty much clear to all of us that more substituted alkene will be the alkene, and always 3 degree, 2 degree, 1 degree will be the order. See, 3 degree, 2 degree, 1 degree. Then we have some very important reaction with us, everyone. So guys, always remember that some of the more dehydrating agents are here, and usually these reactions are following what? They will undergo E2 elimination. So we have Sedzev product in case of Al2O3 heat, P2O5 heat, and also gives Sedzev product. But THO2 thorium oxide with heat gives you Hofmann product. So I'm just star marking it in order to just remind you when the examination comes. And if you are not willingly knowing this part, then you may attempt a mistake, may score -1 instead of +4. So better take this idea. This is something about elimination reactions of alcohol, and these reagents are highly important. Why am I not giving you the mechanism here? Not required actually. The every single process occurs in the similar way. Initially we will be getting a protonated OH group, which will be absorbed by Al2O3 alumina, one of the what I can say hygroscopic reagent. And once it accepts water, then the carbocation may be formed. But here carbocation is not formed, and one-step reaction takes place. That's why it is E2 elimination reaction occurring under these conditions. If you are using an acidic medium under heat and 3 degree, 2 degree, 1 degree like that, so this reaction will follow even elimination with the formation of carbocation. Here there is no formation of carbocation take place. I'm moving forward to the next part. We have a question here, and since this will be 2 degree carbocation formed, so yes, it's a good reaction we see. And this is how the first reaction will be taking place, that OH group will be attacking to H plus, water is eliminated out in the first process only. Protonation will occur. Protonated alcohol will remove the OH H2O group, forming a carbocation. This can lead you to the formation of rearrangement may occur here, and this type of rearrangement is called as 1,2 ring expansion. This is also I have covered actually. 1,2 ring expansion will take place. Formation of a 6-membered ring will take place. If you get confused, always remember that the one which is bearing the positive charge will be number 2, and this will be number 1. So 1 will acquire a positive charge here. This is your number 1, and 1 is already connected to one group here, and it is now attached to number 2. 2 is also having a group here. So this is your second. So this is actually a 3 degree carbocation now, and a more stable carbocation now. So now this compound will be getting back attacked by HSO4 minus or water. Anything you can take. Actually, water is more what I can say acidic than HSO4. Sorry, more basic. Water is more basic than HSO4 minus, but still you can take whatever you want. And there could be two possibilities. The one possibility could be over here with the hydrogen, and the another possibility could be over here with the hydrogen, and another possibility could be here also with the hydrogen. So we see there will be like three products we will be getting. One of them is this, one of them is this, and the another one is this. These are called as endocyclic. Within the cycle there is a double bond. This is called exocyclic. This will be the major product because more stable product. ZF product, this is the major. So guys, this is how we use this process, and here I have explained you the mechanism, how does it work. Moving forward, we have some questions with us. Let me try this question. It's a very easy question for me and for all of you who are strictly following me. So guys, this in first step will be converted into a carbocation, and then carbocation may rearrange itself by 1,2 ME shift. Why ME shift? Because it will give you a 3-degree carbocation. Right now it is a 2-degree carbocation. It will go back to 3-degree carbocation and will make a compound like this. So then right after coming with water as a base, elimination reaction will occurring, and hydrogen will depart. Like this, and this is the alkene we will be getting. So we were not even expecting this alkene, but yes, this is the final product. It all depends upon the rearrangement. Then if you see that the compound is entirely changed, this is all happening because of the rearrangement of carbocation. We have one more question. List the following alcohols dehydrated most readily. So guys, you all know the rate of reaction is directly proportional to, because this is C, even elimination is there, it is proportional to the stability of carbocation. Where can you find this most stable carbocation after removing OH group? I guess this is correct, because this group does what? Plus M over minus I. This group does minus I over plus M. This group does minus M over minus I. And this, there is no group such as such. B is the correct answer. So I want all of you become as much as comfortable as I am, and this will take you some hard work as of now, but believe me, you will become very confident while you will be appearing in your examination. And as of now, which we can see that hardly a month is left for us, so it will be highly beneficial for you. This will be highly benefited, and all the aspirants which are watching me, they will be very much benefited by this lecture. And alcohols, we have covered it already. Now we'll move forward to phenol right after it. Chemical reactions are still on. Your rate of hydration of alcohol follow. It's a even reaction, and it usually like it could be even or it is E2. They all follow 3 degree, 2 degree or 1 degree. Elimination reactions follow this only. So 3 degree, 2 degree, 1 degree, and ethanol. And this doesn't go undergo. This doesn't go. No elimination, because actually it's a beta elimination. There is no beta carbon in it. One other simple question is here. Very simple question here. First of all, make the carbocation. So here is a carbocation. We all know that whenever carbocation like positive charge is on the carbon next to the ring, then 1,2 ring expansion may occur, and also there is a possibility of stable ring formation. Then only it happens. So it is 1,2 ring expansion, and it forms a compound like this. If you face any doubt, name them. Name this as number 2, this as number 1. Now 1 has been removed. Wherever the 1 is removed, it will acquire a positive charge. It's 1. And let's say this is 2. 2 will be happening. It will directly connected there. So now you need to give. So that's it. So in the next step, water will come as a base, and it will attack on the alpha or like beta carbon, beta hydrogen, and will give you an alkene like this. So I think C is the correct answer. Please, if you face any doubt, do let me know in the comment section. Argue with me if you find any other option as the correct answer. So this is how you can build your confidence, guys. Don't you just blindly follow, just do the conversation if you want. So the most important part that we have covered under this reaction was actually an elimination reaction. Elimination and substitution is already covered. So now we'll come to the acidic properties. Are you guys ready for the acidic properties? No, wait, no, man. No, we skipped some reactions there. We still have the type 1 reactions going on like this. This will be removed. So we have some of the similar reactions here. Believe me, these reactions we have already covered in our previous chapter of haloalkane, haloarine. You remember reaction with PCl3, PCl5, both follows SN2 reaction. SOCl2 follows SNI reaction. This again follows SN2 reaction. Hydrogen acid follows SN1 reaction. I have completed this part in our previous chapter only. So we'll take a quick look over here and then we'll move forward. The very first of them is reaction with hydrogen acid. This reaction typically follows SN1 reaction because so primary alcohols only undergo SN2 while others go SN1. Tertiary and secondary both do SN1. Order of reactions that would show the acidic strength HI, HBr, HCl, and a carbocation is formed in the intermediate. I'll give you directly an example. We have Lucas test here for alcohols. What is Lucas test? Lucas test says that reaction of anhydrous ZnCl to an HCl, concentrated HCl, with an alcohol produces first a carbocation which may undergo rearrangement and followed by addition of Cl minus. It will give you RCl as the product. RCl is haloalkane, and chloroalkanes are actually turbid in nature. They look cloudy and which a dirty kind of appearance is there. But alcohols, on the other hand, they were very much transparent. This reaction or this particular test confirms the presence of an alcohol. Tertiary alcohols give this reaction very rapidly, instantly the turbidity appears. Secondary do it right after 5 to 10 minutes. For primary, generally do not give this reaction. It takes a long to happen this reaction. So that's why this is how we can predict the degree of alcohol using this test. See, instant 5 minute and this. We have reaction with PCl3, very easy reaction, and just learn it. And believe me, it's SN2 reaction. I already explained you the mechanism in the previous session, but mechanism is not so important under these reactions. Very honestly and truly speaking, mechanisms are highly important only for those reactions in which there could be a possibility of multiple product with and without following the mechanism. But wherever there is no as such mechanism required, try to just remember the reagents required, attacking reagent is what and product is what. That is more important for all of us. So we have, because there are like plenty of reactions in organic chemistry, every chemical reaction has a reaction mechanism. But being a JEE aspirant or a NEET aspirant, we are not supposed to learn all the mechanisms. Believe me, it's completely time wasting thing. Only focus on those reactions where questions come from the mechanism point of view, just like Markovnikov's versus anti-Markovnikov's versus we have SN1, SN2, SNI mechanism is important. Elimination reactions mechanism important. Wherever the direct reaction is there and we already know the mechanism type, like this is SN2, we already know that backside attack of chloride ion will take place and this is how a product is formed. So you always remember that 3 equivalents of ROH is used. PCl3 is used, RCl with the product, and H3PO3 will be a substance formed. Now H3PO3 is actually liquid state, RCl is also liquid state. It is difficult to separate these two liquids. The same happens in the case of PCl5 also. So in the reaction of PCl5, we get RCH2Cl, POCl3. HCl is the only gas that departs, rest other are the liquids. So it is difficult to abstract the haloalkane out of it. and it is a SN2 mechanism, right? But then we use SOCl2 and SOCl2 thionyl chloride. Whatever the byproducts are produced, these both are gases and they eliminated out, and that is why it has been said that it is the best reagent, see, to produce the RCl, because rest of the members are gaseous, they will eliminate it out. And this follows SNI mechanism. That means retention of configuration takes place. Retention means the leaving group and the attacking group will come to the same side. If you introduce pyridine in the reaction, it becomes SN2 instead of SNI. Then inversion will take place. See, inversion, the leaving group and the attacking reagent are coming from the different sides, opposite sides. Walden inversion is observed. Why am I going a bit fastly from here? Because this is something that we have already covered in our previous session, so there is no point of wasting the time. We'll move forward right from here to some questions. When alcohol react with SOCl2, it gives you what? With SNCl2, it will give you simply retention of the configuration because it follows SNI. The order of reactivity of the alcohol toward HCl, direct proportional to stability of carbocation. So now you remove the OH group and make the carbocation like this, and then try to balance the stability. I guess fourth is the best, followed by third, 4, 3, second and first. This is the correct answer, because fluorine is actually introducing a minus I effect here, so minus I is actually greatest here. What reaction is this? SOCl2 simply SNI takes place with the retention of configuration. SOCl2 pyridine, in presence of pyridine, a ready-made as Cl2 minus will be observed using pyridine. So SN2 reaction will take place. Inversion of configuration will be seen. Where can you find the inversion? I can find the inversion over here. B. Next type of reaction involving the breakage of OH bond is actually the acidic nature. Will represent the acidic nature of alcohols. So acidic strength of alcohol is 1 degree, 2 degree, 3 degree. Because what happens, a carbon ion will be formed after removal of the H group. If it removes HH positive, it will give you CH3, CH2O minus. We call it alkoxide. Like this has become ethoxide. Ethoxide is showing you positive I group. And we know positive I is actually misbalancing it because it's a negative charge, and already negative charge is acquiring electron density from other groups, will become more unstable. The same thing will be happening here. This is having more plus I, and here it's like very much plus I. It's like too much of plus I, so it is disbalancing it. We have some good reactions as an acid, so try learning them by your own. So alcohols can react with metal and they can produce this, but alcohols are actually weak. Alcohols are actually weak acids, even weaker than water. Even weaker than water. So guys, remember, this is the acidic strength order. Methanol is most acidic out of these all, then comes water, and then comes rest of the alcohol. This is the order of their acidic strength. Now you don't need to worry about this concept or wondering, because this part of acidic and basic strength has been told by me in your one of the previous chapter of GOC called as applications of electronic effects. So K will be all following this order. Now out of this order, my question was that metals can react with releasing the hydrogen. This shows the acidic property, but it doesn't give you sodium carbonate test. Doesn't give sodium bicarbonate test. It doesn't give you sodium bicarbonate test because that is given by all the acids which are even stronger than phenol, and phenol is more acidic than alcohol usually, because in phenol the negatively charged ion can be balanced by phenoxide ion, can be balanced by resonance of benzene ring, but in alcohol even it was misbalanced by the R group present in the alcohol, which was creating a positive I effect and increasing the electron density on oxygen as a negative charge. So that was not a stable at all. Then we have reaction with organometallic compound. Since it has an acidic hydrogen, this acidic hydrogen is eliminated and RH will be the product, R dash H. So alkane will be product. Alkane will be the product. Another reaction is called as esterification reaction, and this reaction is also called as Fischer esterification. Wow, yeah. So guys, I'll give you an idea, and believe me, you will be pretty much comfortable after knowing this reaction. So what we have is, we have one alcohol, ROH, we have an ester, R C double bond O, OR dash, and let's say this is double OR dash, this is single R dash. This reaction takes place in acidic medium, and the product of this reaction will be C. So we usually think that, no, yeah, this is correct, OH. We usually think that this is acidic, and RC double bond O, OH plus R dash OH. Now it will look like better. So guys, do need to you only need to know that this is not an acidic reaction which is taking place from this acid. Instead, it's a SN2TH type reaction. It's a SN2TH reaction. It's a SN2TH reaction, and you all know SN2TH reaction is given by all the carboxylic acid derivatives. So this is how it reaction takes place. So you need to remove the OH part of an acid and H part of the ROH. So now by removing water, your final product will be C double bond O, OR dash. So let's say this is O18. So guys, this will be O18. That is what you know. And then H2O will be simply eliminated out. So we are getting ester as a product. This is ester as a product. So in case of any confusion, you can ask me whatever you want. I'm giving the best way to learn it, and we do not have too much of time to do the research about these reactions. Just simply take the idea. You must know where it is the reaction taking place. We have a proper mechanism here, everyone, for which you just go through, but always remember, this is the outcome of the mechanism, that H from ROH, OH from HCOH will go, and rest of the product will be maintained by your own. This is the outcome of the mechanism. Now please learn the mechanism and write down it and learn it immediately right now. And now allow me a couple of minutes. I'll be coming back after bringing some water for me. Yeah, guys, so let's continue from here. We had this reaction, esterification of alcohols, and this reaction is actually showing us the acidic nature of alcohol. So, however, we know that carboxylic acids are better acid, stronger acid than alcohol, but still, alcohol is showing the acidic nature because this reaction is actually not acid-base reaction. More or less, this is SN2TH type reaction, and that's why reaction products are ester. Now we will move forward and we'll come to a question. According to Lee-Shatley principle, esterification is driven to the product side by excess of alcohol. Yes or no? Right? If reactant is increased, if the concentration of reactant is increased, reaction goes forward. Very interesting question here. Very interesting on the mechanism based question. But we already asked smart people, we will remove the H from here and OH from here. So our product will be C double bond O18, C double bond O18, and then this whole CH2, CH2 like this. So this is our product. The product will be, so see, this is acidic hydrogen is there, R minus goes on attack, and the product will be RH, R dash H as an alkane, plus the byproduct will be magnesium attached with halogen and OR coming out of this alcohol. Correct answer should be alkane. No, why somebody is writing me that sir, please be energetic and take some water. Shivani Mehta. So first of all, I would like to thank you for your suggestion, and then I would like to interrogate and want to ask you that who asked you your suggestion? This suggestion is not welcomed here, everyone. The only important part out of this lecture is whether are you understanding what I'm teaching over here or not. We're not supposed to take any random suggestions like be energetic or do dance or do this step, and not strictly welcomed in terms of suggestions. And you all people know that we work very hard. Even on the Sundays we are teaching you. It's absolutely free of cost. And on the return of that, if you add some valuable feedback, like conducting of PYQ sessions or practice sessions or explaining some part which you are not getting, it's absolutely fine to me. And we can explain that part. But coming illogically without, like with these kind of explanations, bring energy to dance, hook steps, not welcomed at all, won't be taken as a suggestion. Let's move forward then. So I think now you will be feeling more energy. Shivani Mehta. Here is a question. Here is a question. We have one reaction in which esterification is looking like to happen. No, we have what reaction is this? Yeah, not getting is exactly okay. Got it. So initially, this OH group will be departed, and the hydrogen will be from here, and the first product that we'll be getting is this. This alcohol will not be affected. It will become an OC2 OET will be the product. Now this reaction on SOCl2 and heat, thionyl chloride and heat will give you chloro compound. So this will be a chloro compound with ester. I think C is the correct answer. We all know this reaction, SNI product. Chloro will be the product. OH will be removed by Cl, substitution reaction. One question, a liquid was mixed with ethanol and a drop of concentrated H2SO4 was added. A compound with fruity smell was formed, no doubt. So first of all, liquid was mixed with this, and fruity smell is actually of esters. Where I can find the esters, by the way? And we don't have any esters here. So the liquid, okay, liquid was no doubt an alcohol, because the reaction of alcohol with ethanol and in presence of H2SO4, heat give you CH3COO OET ester with fruity smell. Chaliye. Now let's move forward with one more question. We have mild oxidizing agents which will be working on alcohols to give the carbonyl compound, expected carbonyl compound. Like primary will giving you aldehyde, and secondary alcohol will give you ketone, and tertiary will not be oxidized. So like that. So we have PCC, pyridinium chlorochromate, one of the mild oxidizing agents. Just simply learn and also learn their structure, how are they formed. Sometimes it can be given with the term PCC or pyridinium chlorochromate, or sometimes it can mention you the reagents. So this is pyridine and this compound is called as chlorochromate. So this is pyridine dichromate also. So pyridine like dichromate, K2Cr2, potassium dichromate, strong oxidizing agent. Pyridinium dichromate is a weak oxidizing agent. Then copper at 573 Kelvin is also working as an oxidizing agent. And we also have Collins reagent called as dipyridine chromium. Dipyridine chromium is pyridine. We have twice of pyridine, CrO2 and then CH2Cl2. CH2Cl2 is the medium in which we are like taking this reaction upon. So strong oxidizing agents are, we have strong oxidizing agent in the category of KMnO4, K2Cr2, an acidic medium, and then nitric acid also. Concentrated nitric acid HNO3 can also be a strong oxidizing agent. This is fourth. We have Jones reagent in which we use CrO3 and aqueous H2SO4 and acetone. In acetone we specifically use it. This is also called as glacial acetic acid. Now, what glacial acetic acid is a bit different. So glacial acetic acid is actually acetic acid in its high concentration, no water. We have oxidation of primary alcohol. So primary alcohol with mild oxidizing agent gives to aldehyde, strong will be converted to carboxylic acid. So just take this thing as an idea that the carbon atom which is connected to the OH group will also be having some of the hydrogen group which are converted to OH group, and right after conversion into OH group, the two OH groups are unstable on one carbon atom, elimination of water will take place and C double bond O group is formed. Here we have mild oxidizing agent, one of them will be converted to OH, and here both hydrogen will be converted to OH and then carboxylic acid is formed. So an oxidation of alcohols with respect to so many reagent is given here. We have PCC, PDC, Collins as weak. So weak reagent will produce you what? These are aldehydes is the product, and then we have strong oxidizing agent. They will produce simply the carboxylic acid as a product. Since the reaction is carried out in basic medium, this is converted into CO minus rather than going to COH. This is a very easy part. Then oxidation of secondary alcohol we have. Secondary alcohols are oxidized, whether mild or it is strong. It can have only one option, converting H into OH. Two OH group on one carbon are unstable, water will be eliminated out, and C double bond group as in ketone is formed as a product. So guys, if you are bringing this reaction under drastic conditions, then it can lead you to formation of the smaller acids such as this, that's CH3, let's say we are using concentrated HNO3 and heat, then it is formed like this, or this can further be oxidized to, that is a product, ultimate product, final oxidized product will be this. I think you are getting this concept very clearly. Final oxidized. Next, so now oxidation of 2-degree alcohol was going on using weak oxidizing agents or strong. It's directly converted into ketone. Also, secondary alcohol upon oxidation with strong oxidizing agent under conditions is we're done it here. Then oxidation of secondary alcohol. Okay. It can go to enol form and then it can undergo oxidation under drastic condition. We have oxidation of 3-degree. It doesn't work with 3-degree because 3-degree doesn't have any oxidizable hydrogen which can be converted to OH, so there is no reaction. But under hot copper, hot conditions in presence of copper, an elimination reaction may work and an alkene will be formed as a product C. Where is alkene? Isobutene along with the elimination of water. This is actually happening the elimination reaction rather than the oxidation. Working of MnO2. MnO2 is also a oxidizing agent, but it's a selective oxidizing agent. How does it oxidize? It actually oxidizes to vinylic or allylic. Let me check it. Yeah, allylic alcohol. So MnO2 is actually a selective oxidizing agent used for primary and secondary allylic and benzylic alcohols. Primary alcohols yield aldehyde and secondary yield to the ketone respectively. So this is one example. So this OH group will be converted to C double bond O. This is OH, C double bond O will be the product. So guys, this is how it works. In benzylic and allylic, both systems, I told you they are alike system in which one sp3 hybridized carbon atom directly bonded to OH group will be connected to a sp2 hybridized carbon atom, and that is how the reaction works. So this is something that you have to make the notes about. We are not supposed to fall into the reaction mechanisms of under these reactions. We simply need to write down all the chemical reactions one by one. We need to take this idea that where we are supposed to use this product. MnO2 is an oxidizing agent, but again, it's most importantly a selective oxidizing agent. It doesn't oxidize all of the alcohols. It only oxidizes to allylic or benzylic alcohol. So that's what we have to take in the idea. So now try this question. We have pyridinium chlorochromate, which is a weak oxidizing agent. So what does a weak oxidizing agent do? Alcohols will be converted into aldehyde. And this will remain undisturbed because tertiary doesn't undergo oxidation. So only CHO functional group is there. Yes. One OH functional group is also there. Yes. This is the correct answer. Because see, you can check it out. One OH group is there, one C double bond OH group there. One is CHO, another one is OH in the final product. Then we have one interesting chemical reaction called as Pinacol-Pinacolone Rearrangement. Let me check if there is any, nothing is given to us here. So guys, I'll explain this part, Pinacol-Pinacolone Rearrangement. So what is Pinacol? Pinacol is actually vicinal diol. We have a vicinal diol. So guys, this reaction happens in acidic medium. So we can see that dilute H2SO4 sometimes is used, and this reaction occur in such a way that Pinacolone is the product which we get. So this is how we get the product. Now this vicinal diol is called as Pinacol, and this is called as Pinacolone. Okay, I'll explain it using a mechanism. So guys, I have plenty of things to explain, but before that, okay, thank you, Ninad. So we have an important reaction here. Let's say this is a carbon. It is connected to OH group. We have a benzene here, and benzene with, let's say, OCH3 group. We have another benzene here with simply benzene. This carbon is attached to another carbon which also has a benzene. Here is the OH group, and let us suppose one is the hydrogen. This is the perfect example I can give you, and now let's see how it works. Let's say this is also similar kind of thing. Two benzenes are attached. Now it has become a perfect question to take about. So guys, in first reaction, H plus will come. There's two possibility which one should go, this one or this one. So basically, wherever the carbocation is most stable, that carbon atom, that OH group will work. Okay, where more stable carbocation is formed, and we all know that after the attack of H plus, H2 will be departed. So which should be the correct more stable carbocation? Here it's OCH3 group which will providing you positive M effect. So definitely this will be the more stable carbocation. One benzene, one carbon, one benzene with OCH3 group. We have a positive charge here. Another carbon also has two benzene groups attached to it. But the beauty of this reaction is that so formed carbocation wants to take the stability of this OH group, because O directly can introduce its lone pair to the carbon atom. So that's why there will be 1,2 phenyl shift will take place. So guys, see, now this will follow the shift will follow the migratory aptitude. Means whatever is having the higher electron density, that will go for the shifting. But again, you all must know that we have two similar groups, so anyone can go. So the correct product will be the final product from here will look like this. We already has a benzene and this carbon which was earlier having a positive charge. Now a benzene has come here, and then benzene has attacked over here, and it has become like this. And this might not be having that much degree earlier, it is 3 degree already, but now OH group is actually giving it the support of this resonance, and that's why it is making it more stable, and the another group is already existing benzene. So finally from this, now deprotonation happens, and deprotonation happens in such a way that this electron density departs like this. So it's deprotonation. So guys, this is acid catalyzed mechanism in which first it is added, then at last it is removed. It is called as acid catalyzed mechanism. The final product will be looking like this: OCH3, benzene, carbon, one more benzene, two pH groups are here, and then it is containing double bond O and with another benzene. So this is called as Pinacolone. And guys, I hope you all have got this concept. With using this mechanism, you can please go through this reaction and can identify where what has happened, which reagent has to attack, which has to acquire the positive charge. We had two options to acquire the positive charge. Right after the formation of a positive charge cation, we had 2 or 3 options of rearrangement. We still did the rearrangement. We sent according to the migratory aptitude. This is something migratory aptitude has been already explained by me, the rearrangement of carbocation, under the section of GOC day 3, where I was teaching you the applications of electronic effects. But don't worry, I also have come up with this information over here also. This is your Pinacol-Pinacolone rearrangement. This is an easy concept, and it's a very likable concept. It's something which JEE people favor and maybe asked in your coming exam. So that is the migratory order I was explaining you. So this take the idea that hydride has the most electron density. That's why hydride goes at first, then phenyl, and then we have 3 degree, 2 degree, 1 degree, and any phenyl which is substituted with electron donating group will always be greater than even hydride, and then phenyl which is connected to electron withdrawing group, like that. It's a question given to us. So now does anyone want to submit with the answer for this? I'm waiting for the answer. Please try it by your own. Wait. I have received so many calls. Give me a minute, and you people try this question by your own, everyone. Please try it by your own. हाँ लोकेश. हाँ तो ठीक है मैं 1 मिनट बाहर आके करता हूँ. मैं एक्चुअली मेरे लेक्चर पर 11 बजे ही मैं आ गया था. बात कर लेता हूँ.
So guys, let us. So I gave you this question and I was expecting you people to respond me. Anyway, let me give you the correct answer. Please be focused while I'm giving you the explanation because it requires proper mechanism to follow. Otherwise, we cannot predict the product. These are the question where mechanism is followed. So what we'll do, and of initial first, most stable carbocation will be formed. So this OH group, this will attack. Removal of water will take place. pH, CpH with a positive charge will be formed. This carbon atom is also having this much. But we all know that positive charge wants to get adjacent to the OH group in order to get the most stable carbocation stability and resonance of O minus, O lone pair. So it will go, it will do 1,2 Me shift. 1, Me shift. So Me shift will go and then this methyl will attack here. This is your one of the methyl. This is your OH. And now the positive charge is appearing here. At last, H will be deducted out. It's an acid catalyzed mechanism. Initially, H plus is utilized. And lastly, H plus will be removed out. So this is how your final product will look like. Pinacolone is ready, everyone. Pinacolone is ready to serve. That's your final product. We have one more important reaction, and this reaction needs to know the name itself. It's Oppenor oxidation. So guys, if you do this reaction where we are taking acetone as a one of the reagent, so secondary is this a reaction of 2-degree alcohols with acetone. This reaction is called as Oppenor oxidation, and the reverse of this reaction is called as MVP reduction, Meerwein-Pondorf reduction. These are two naming reactions, and in Meerwein-Pondorf reaction we will be having one isopropyl alcohol with this isopropyl alcohol OH, and this is a random ketone. Take this idea and no need to learn or going through the mechanism part. Simply learn what reagents are used, what product will be formed. That's it. And under what we commonly use the bases such as aluminum, tertiary oxide, aluminum propoxide, etc. Then we have periodic acid, periodic acid. Sorry, periodic now. Wow, yeah, the spell is the same. It's actually periodic acid. So periodic acid is HiO4 and it cleavages the vicinal diol. So wherever you find this kind of combination, so under the presence of HiO4, the mechanism itself works like this, that it cleavages and produces you C double bond O plus C double bond O, like that it works. So anyways, you can learn that wherever it cuts out this bond, RR bond with vicinal diol, it provides extra OH, and that's how the product will looking like. We have one mechanism over here also, but I again told you not required, not strictly required to learn down. We just need to understand how it works. I will also give you one more thing to understand, that if a group like this is there, this also under the influence of HiO4, heating will give you like this. So this is how it look like. So 1,2-diol are getting converted into a ketone as an elimination of water. This is Pinacol-Pinacolone rearrangement. Then intermediate carbocation is more stable in Pinacol-Pinacolone rearrangement. Which intermediate carbocation is more stable in Pinacol-Pinacolone rearrangement? Intermediate carbocation, I think 3 degree. What do you think? 3 degree will be more stable. Why first carbocation should be made the most stable? That is the RDS, because the first is the RDS of the reaction. Formation of the carbocation is the RDS. So rate determining step, if has the most stable intermediate formed, then no doubt it will give you the most stable product as well. We have one important question asked back in JEE Main 2019. So JEE Main 2019 asked us the question upon Pinacol-Pinacolone rearrangement. So guys, this is something which I have explained you in very detail using proper mechanism. And now my question is to all of you that please try this question and give me the answer. And even with Satish Kodeti, my question is to you, please submit me the correct answer here. We already have covered this part of the reaction. Now I'll explain you later on, but right now you apply the concept by your own. So what it is required is the proper explanation of the concept, not the energy. Sir, energy. You show your energy in solving the question. Give me a correct answer. So that is the problem with us actually. We all people know that how can we basically put the mistakes of someone, how can we get into the negativities? We are not getting the best part of this lecture, which is the proper explanation of every concept. Pinacolone was asked in JEE Main 2019 and can be asked this year also. Let me give you the correct idea. Both of them are symmetric, whereas whichever the OH group you are picking, both of them are the symmetric. Take anything, remove the water part and make a carbocation. Make a carbocation. So this is actually your OH part, and to this we have a positive charge here now, like this. In the very next step, what we can see, the only possibility of rearrangement, neither we have a positive charge like hydrogen here, we only need to do shift. What kind of shift? 1, 2, like this. This will shift like this. So this will become 1, this will become 2. As I told you, how does it work? 1, 2, ring expansion. Because wherever the bond is breaking from 2, this will be acquiring a positive charge, will be stabilized by this OH group. So this will become a 6-membered ring. It's a 6-membered ring, and this 6-membered ring is having a positive charge here. Now this is your 2 and this one is 1. This is, let's say, 2. This is a 6-membered ring. Let's say this is your 2 and 2 which OH group is there and it's a positive charge. So numbering will be 2. So where will 1 go? 1 is directly coming to here. So what I can see here, a 5-membered ring like this with 1 over here. That's it. So that is how it look like. And the next step, one of the hydrogen will be eliminated out like this, and it will become an alkene will be the product. How? Here, not alkene, sorry, this will be a pinacolone. This is the correct product. Now, can you find such product over here? As I see, I think B is the correct answer here. Now, let me check. Okay, great, Satish. Keep it up, guys. B is the correct answer. Those who have submitted with the correct answer, you truly deserve the +4 marks. Let's go. We have one more question. Which of the following are not cleavaged by HiO4? So guys, HiO4 only does the cleavage for vicinal diols, and if there is 1,3-propanediol, so there is no cleavage, as it doesn't suit to the the cyclic mechanism given over there, and this will not undergo any cleavage. We also have 1-methoxy 2-propanol, 1-methoxy, 1-methoxy, so OCH3 is here, and 2-propanol. No, this will not go under cleavage, only OH goes. So I think first and fourth are not eligible. Sorry, third and fourth are not eligible. Third and fourth, D is the correct answer. Sir, alcohol directly attached to double bonded carbon. No, not like that. It should be a general vicinal. Vicinal is fine, not a doubly bonded. There could be another product that can be formed in case of doubly bonded. Even the product could go to the oxidative cleavage and can produce you alcohols, acid in the result. You don't remember that reaction which we used to do in oxidative cleavage of alkenes? So the final product will be a carboxylic acid in that case. Here the final product is in ketone or aldehyde, and what we are doing, the cleavage HiO4 cleavage for vicinal diols. So the same reaction can work for the doubly bonded vicinal diol also, but in that case carboxylic acid will be the product. Now let's move forward with the one more question. I think this is the similar question. So it is again Pinacol-Pinacolone reaction. So I will give this question as a homework to all of you. It's same Pinacol-Pinacolone reaction or rearrangement. So I am giving this question as a homework because I have solved similar so many questions. Now it is your turn to solve it. And guys, with this, we right now have entered to the another era of another important compound called as phenol. So I took literally 2 hours to completely finish alcohol. But alcohol is the biggest portion of entire chapter because alcohol contains so many reactions of its preparations and as chemical reaction. Now phenol is also very important part, but relatively the number of reactions will be lesser. So let us start with phenol. First of all, what is phenol? So guys, phenol is actually OH group which is connected to, which is substituting the hydrogen of a benzene ring. This is how phenol look like. This is your monohydric phenol. This is dihydric phenol, trihydric phenol. Like phenol is something that comes under the category of AROH. AR is the arene group and OH is the alcoholic group. But they are highly different from each other. We have some set of important compound for which their common names have been accepted as the IUPAC. Take this example: catechol, resorcinol, quinol. We have orthocresol, metacresol, paracresol, and there is one more compound, guys, maybe not mentioned here. I'll give it to you. It's a benzene and it's 135 OH, and we call this compound as fluoroglucinol. So these names are actually IUPAC names only. These common names have been accepted as IUPAC. We do not write their IUPAC name and we do not apply any rules. Their common names have been accepted as IUPAC. Fluoroglucinol, nice yaar. Sir, once again explain the previous question. Which one yaar? This question or this question? Which question you're talking about? Where was the question? This one though, it's a homework, you tried. And here I told you that 1-methoxy 2-propanol. So OH group should be there, not OCH3 group, first of all. And there is one, it's not 1, 2, it's 1, 3. So 1, 3 is not allowed to go under this. Like that. Now coming back to our ongoing topic, we have fluoroglucinol. So now introduction to phenol is ongoing and there is a partial double bond character in this and zoop. So yes everyone, phenol in its property has OH group attached to it, and that makes phenol as a good reagent for electrophilic aromatic substitution reactions. So let us suppose this is our phenol. So OH, and since we all know that this OH group is working as a positive M group, the displacement can occur like this. First, I'll make all the so formed structures a negative charge and a double bond, and then O and then H with a positive charge. Then we have similar things here. So I'm drawing the resonating structures of phenol here in order to show you where do we get the negative charge, so that you will get the electrophilic aromatic substitution reactions once right after this. Now let's see how is electron moving from one position to another. See, then in the next step, so these 5, 1, 2, 3, 4, 5 are the resonating structures of phenol, and we can see that this OH group is actually, this is plus M group, and it is electron plus M or electron donating group or electron releasing group, which is ortho para directing towards electrophilic aromatic substitution reactions. So anyways, I'll come to that part, but right now I have explained because it was given. Sir, why only 1, 2? Because only 1 and 2 had vicinal diol, which is the need of getting cleavage by HiO4. Vicinal diol means 1, 2, 2, 3, 3, 4, but they should be adjacent to each other. In propane 1,3-ol, 1 and 3 position were occupied by OH group. Second was empty, that's why it couldn't cleavage it as per the mechanism. Also, in the another case, we had one of them was methoxy group, OCH3, another one was OH group. We only need ols alcoholic group. That's why 1 and 2 only did this. I hope this part is now clear to all of you. So that's why I say that, see, sometimes we need to remember what exactly is given to us. What do we have to apply? We are not supposed to fall into the mechanism part of cleavage by HiO4, cleavage by hot KMnO4, cleavage by HI and heat. Always focus on what reagent has been given, where we have to attack, what we have to make as a product. That is what it is needed, because there are some reactions like Pinacol-Pinacolone Rearrangement where we cannot identify the final product without undergoing the step-by-step mechanism. There we need to apply the mechanism. Wherever these kind of reactions come where directly reagent is used somewhere over a given substrate, this is how we have to make the product. We have to learn these sequences only, that we have to attack on this, we have to attack on this. This is how it is formed. Anyways, now where were we? I got distracted. So what I was explaining is a point over here that sp2 hybridized state of carbon in which oxygen is attacked creates an electron density upon the system, and that's why OH group over phenyl ring works as a electron releasing group. Now let us come to the preparation. Now we do not have anything in meanwhile. Yeah, we have preparations. Preparations are already explained under AR-SN reactions, you remember? Aromatic nucleophilic substitution reactions. In the previous chapter we studied once. One of them was Dawes process, DOW Dawes process. Dawes process involves the attack of NaOH as AR-SN2 reaction under strong higher temperature and pressure. So this reaction can become easier if we attach some electron withdrawing group to this chlorobenzene. So halobenzene is being attacked by the NaOH under high temperature, high pressure, because this reaction usually doesn't occur at random normal temperature. This reaction is called as AR-SN reaction. We also have this partial double bond over here, due to which this bond doesn't breaks easily, and that's why it needed high temperature, high pressure. This is partial double bond. So there happens addition elimination reaction, and the product will be ONA because the medium is basic. Because of the NaOH, it is O minus. So now if this undergoes in acidic medium, dilute HCl, it will give you what? Phenol as a product with NaCl. The mechanism of this is being covered into alkyl and aryl halide chapter. Dawes process mechanism is given. So as I told you, this reaction is actually, sorry, this is elimination addition reaction. So this is benzene intermediate is actually called as elimination addition. So first OH is eliminating out H, triply bonded is counted, then addition of OH minus takes place at both Cine and same side attack. This is one part. This is one part which has been done. Dawes process, presence of preparation of phenol from the chloro or bromobenzene or halobenzene in the presence of high temperature, high pressure. This reaction can do easily if there are presence of electron withdrawing groups which can ease out or which can help to remove the hydrogen at faster rate. Then from cumene, we have from cumene, I must mark it as a star because this is most important reaction that has been asked previously, and not from the point of view of JEE Main but also from your board's point of view. Whatever the exam you give, this reaction is highly important, called as from cumene peroxide. It is industrial method. It is produced in bulk. Phenol is produced in bulk. So cumene is called as isopropyl benzene. This is your isopropyl benzene. The hydrogen to which first gets oxidized by O2, and this OOH is formed, which is a peroxy. So this is called as cumene hydroperoxide. Cumene was earlier compound, now it has become cumene hydroperoxide. On the attack of H2O happens in such a way that this reaction, this will be attached by this OH group, and C double bond O CH3 will be formed as a acetone. So I'll show you one question here. Again, no need to run down the mechanism part, only need to take the reactions into account, that this is formed, this has been attacked, this is the final product. That's how we have to learn it. This reaction is called as industrial preparation of phenol, and you will find some good reaction also. See, this is the mechanism, but I told you not to remember this reaction because there are no multiple variations can be created in this reaction. So that's why I would ask you to learn a single line reaction. Cumene hydroperoxide, attack of acid, it gives you phenol plus acetone. Here is the mechanism given, no need to learn, not required, but still I have this for you. Those who are preparing and those who want to learn it, they may, but I personally recommend not required, not necessarily needed. We have another reaction called as benzene sulfonic acid. Guys, always whenever we were doing the sulfonation of benzene, it has been said that it's a reversible process, because from benzene sulfonic acid, benzene can also be prepared or it can be converted back into phenol. So how are we going to conduct this reaction? We initially have with us this compound called as benzene. Benzene on reaction with H2SO4 fuming undergoes EAS, electrophilic aromatic substitution, forming sulfonic acid, benzene sulfonic acid, which under basic medium and removes the SO3Na, and on heating it produces what? ONA plus Na2SO3. This is an important reaction that we have to learn. This under acidic medium can produce you phenol. Now learn this reaction. Guys, another important reaction is using diazonium salt. We know how diazonium salts are prepared. Diazonium salts are prepared from aniline by treating it with a nitrous acid HNO2, which can undergo disproportionation, creating nitric oxides and nitric acid. So that is why this reaction is carried out by freshly prepared HNO2 on reaction with Aniline gives you diazonium salt, which is stable only under 0 to 5 degrees Celsius. And then on simple warming in presence of water produces the phenol, an oxidized product. And then nitrogen and HCl will be the byproduct. Decarboxylation is another important example. Decarboxylation, soda-lime decarboxylation. This is called as soda-lime decarboxylation. Soda-lime decarboxylation is something that which we have already covered. This reaction is important to create the alkanes, and alkanes are created by the salts, or like carboxylic acid can be taken. Carboxylic acid and its sodium and potassium salts under the influence of CO and NaOH produces RH as the product. So this is R, CO2 will be eliminated out. That is why it is called as decarboxylation. Carboxylic group is removed and H will be attached here. So this is how phenol is prepared. The simplest phenol is C6H5OH and it is also called as. So guys, it's a common name and there is nothing that I can give you the explanation of. We can simply take it as a carbolic acid, okay? Because carboxylic cannot be carboxylic, we all know RCOH. Carbolic acid, we also call it. Phenol can also be called as carbolic acid. Okay, next. Here is a reaction, and a very important one that we just studied, that cumene on reaction with this gives you cumene peroxide, and then followed by hydrolysis in acidic medium produces like phenol plus acetone. Phenol plus acetone, C is the correct answer. No need of going through the mechanism and everything. Simply learn. When sodium benzene sulfonate is what? SO3Na. Fused with sodium hydroxide, it is removed as a, it is H2O and it is removed as a Na2SO3, sodium sulfate. So correct answer should be phenol. Phenol is obtained by heating alkaline aqua solution of aniline, benzene, diazonium chloride, benzoic acid. I think this is correct. Benzene diazonium chloride. Because see, aniline will not do any reaction in basic medium because it is already, aniline is basic in nature. Benzoic acid can also form sodium benzoate, which is a salt of acid base reaction, but only this reaction under heating, and we are providing it NaOH dilute. So this will give you what? ONA plus N2 gas plus HCl, and then this under acidic treatment can give you phenol. This is phenol. One more question. Decarboxylation of sodium salicylate will give you what? Sodium salicylate. But what is sodium salicylate? Salicylate is actually this. Sodium salicylic acid is this. CH3COH is called as salicylic acid, and O minus Na plus is sodium salicylate and with benzene. So this compound on NaOH plus CaO on heat, soda lime decarboxylation. So CO2 group is eliminated out in the form of Na2CO3, and the remaining compound will be O, simply C. This is your final product. Correct answer should be phenol. That was a part where we prepared phenol. Preparation of phenol is now completed. I will cover this part, physical and chemical properties. First, we will complete the physical part. Then we will take a short break. And let me see, where is my food? Then we'll come back and we'll rejoin, and then we'll finish the remaining part of this chapter. but it is showing will be delivered in 28 minutes, so it seems like it's taking too much of time. Okay. Okay, now we have a question. We have then physical properties and chemical properties. So first of all, we'll understand the physical properties, and then reactions of phenol will be completed. Guys, this is what you can see is general oxidation reaction, then hydrogenation reaction, then we have reduction with zinc, and then we will having these reactions as a these all reactions are electrophilic aromatic substitution reactions. And one of the very important part of this chapter, because from this frequently some of the questions have been asked previously. And let us start then. We have first physical property. So guys, both alcohol and phenol are water soluble because of their ability to form the hydrogen bond, but phenol is less soluble because the higher or the bigger benzene, or this what I can say, this carbon hydrogen group, which is hydrophobic in nature, and due to the same reason their boiling points are also greater than the corresponding compound of molecular mass, except carboxylic can usually have higher. So like if we talk about a random order of boiling point, so the random order of boiling point could be general order of boiling point. Okay, so if compounds are of similar molar masses, then the most boiling point is occurred by carboxylic acids, because carboxylic acids has more number of oxygen, which can make the more number of hydrogen bonds with similar molecules. Then we have alcohols. Then we have like they have similar kind of attraction, like they could be ethers and nearly equals to this haloalkanes. RX also have the similar one. And then at last we have alkanes. Alkanes have the least. Alkanes have the least boiling point. This is the order of boiling point. Clear? We have acidic nature of phenol here. So guys, since acidic and basic behavior of all the organic compounds have already been explained by me in previous sessions of GOC as an application of this electronic effects, and I'm not asking you to go back there and practice. I will explain it over here also. But the thing is, whenever you come over here on this chapter, it is recommended that follow everything of the chapter of organic chemistry in sequence. First go to GOC, then application of GOC, then reach to the reaction mechanism part, isomerism part, and then come to the haloalkane haloarine as a part of 12th standard. Then reach over here of the we have this alcohol phenol ether. Then we'll reach to the carbonyl compound amines, and that's how we'll complete our whole syllabus. So usually it has been said that if we compare the acidic strength of ROH versus phenol, so guys, phenol is considered to be more acidic than alcohols, because alcohols on releasing their H positive, they gives RO minus, and since R gives them the positive I effect, it makes this anion as unstable. But comparing to the benzene ring, which is directly connected to a carbon acquiring the positive charge, oxygen with a negative charge, So this is actually reso stable. So this is actually stable, and this is minus I effect is also producing, but more or less this is reso stable. Hopefully this is clear to all of you. So acidic nature, continuing the acidic nature of phenol, we have some set of good chemical reactions that need to follow. Number one is like we have sodium metal. Sodium metal can react and can produce hydrogen gas. All the acids can react with metal producing hydrogen gas and respective salt. So it will be a sodium salt, sodium phenoxide. Similarly, NaOH also reacts with this compound. NaOH produces ONA and then water. Earlier we saw that NaOH was not reacting directly with the alcohols, or maybe it was reacting there. But alcohols are poor or weaker acids than comparing to the water. If acidity of phenol we are talking about, like the acidic strength of phenol. Phenol, if it is attached with an electron withdrawing group, it makes it more acidic in nature because its conjugate base will be more stable in that way. Oxide phenoxide ion can be stabilized by electron withdrawing group, and similarly if we are giving it a electron donating group somewhere, then it will give it less stability and lesser acidic strength. I'll sit for a while and I'll explain everything sitting over here. So guys, see, electron withdrawing group actually helps to delocalize this charge, and electron donating group actually making it less stable. Now idea what is happening here, yeah. This is also electron withdrawing. Electron donating group is actually unstabilizing it. Electron withdrawing groups such as withdrawable substituent disperse the negative charge of ARO minus, making it a weaker base. Yeah, true, making it weaker base and stronger acid to phenol. Which of the following decreasing order of solubility? So guys, what is the increasing order of solubility? I think B should be the correct increasing order. We have been asked increasing order of solubility. So see, B will be having the most solubility because water can easily make the H bond with it like this, and then we will be having C, then we'll be having D, and then we'll be having A, because A has lesser number of OH group, and that's why lesser extent of H bonding with water molecule, and this can be hindered. That's why lesser molecule of water will be attached here, but in that way no hindrance is there. That will give you most solubility. So this is the order of solubility in water. It seems like we will finish our complete phenol, and then we will take a lunch break, and then we'll reach to the remaining part of this chapter, which is ether. Here is a question: among these compounds, the acidic strength will be what? Anyways, we'll try. First of all, we need to write all of them and write their structure also. We have first phenol. We have methyl phenol, where it is dashed. Okay, let us say this is methyl phenol. What is methyl phenol, by the way? No idea, dude. So let us take this para-methyl alcohol. Third one is actually meta-nitrophenol. And then fourth is meta-nitrophenol. Sorry, para-nitrophenol. No doubt fourth will be the most acidic, and how I'll explain. Here we have no effect as such. CH3 does positive H more than positive I. So this is unbalancing, making it less stable, the carbon ion, or this O minus phenoxide ion will be getting less stability because of the presence of this CH3 group, and that's why this is least stable. and NO2 is only doing minus I effect, as this OH group is ortho para directing in nature. Negative charge will be creating on ortho and para. Nitro adjacent to that will only be doing a minus I effect rather than minus M effect. But over here minus charge will be directly absorbed by NO2 and it is having minus M more than minus I. So electron withdrawing group, wherever it is present, it will make more stabilized phenoxide form, and that is why it is creating PHOH like phenol as a more acidic compound. So correct order of acidic strength will become what? I think the fourth one is the most acidic, followed by, we have third, at least something is helpful. Third, first will be coming at third position, and then come the second. Why second? Because second one is making the this phenoxide ion more unstable. The correct order should be this. Now, moving forward with next question. Which of the following will be soluble in sodium hydrogen carbonate? Anything which is stronger than phenol, which will not be benzene sulfonic acid, benzoic acid, 2,4-, I think this is correct, orthonitrophenol. So because, and do not need to worry about anything, because what we see is this is least acidic among all of them, least acidic among all options. So something which is least acidic will definitely be not giving this test, which is the test of an acid. Why solubility of phenol decreases in the size of hydrophobic group? This hydrophobic group is not easily hydrated by the water molecules because of the difference of the bonding. No need to explain it in that way. Let's move forward. Yes, then we have melting point of phenol is relatively high for an aryl compound. Why is it so? Aryl compound, because aryl is bigger in size, more covalent bonding will be there. It will be not hydrogen bonding, it will be doing more covalent bonding. See, melting point of phenol is relatively higher because of the covalent bonding. No metallic bonding takes place, no hydrogen. Hydrogen bonding is common between alcohol and phenol, but phenol is having higher melting point because it's a bigger in size, more amount of what we can see, higher extent of van der Waals force of attraction can be observed, which will be missing in the case of alcohols. Another question is here that phenol is more acidic because its conjugate ion is resonance stabilized. So phenoxide ion is resonance stabilized. That is the correct answer. See, in single line I can give you the correct answer. See, which one is the most acidic compound? What do you think? Sir, we have nothing over here. We have minus M of nitro working more than minus I. We have a strictly minus M here of 3 nitro groups. We have positive H and that then positive I. So if you want me to write down the order, the correct order of acidic strength will become, most acidic is your C, which is called as picric acid. Then we have B, then we have A, and then last will be the D, because D is making the conjugate base or the anion, phenoxide ion, more unstable because of its electron donating nature. A negative charge species already having a negative charge, and they are pushing electron towards it, making negative charge more and more about that molecule or that ion, unstabilizing it, destabilizing it. Here is another question. We have arranged the following compound in decreasing order of acidic strength. Same funda we have to use. We are always having at these para positions, they all are eligible for doing the mesomeric effect. Chlorine has minus I more than positive M. CH3 group has positive H more than minus I, but this is unstabilizing the molecule. Nitro group has minus M more than minus I. NO3H3 have positive M effect more than minus I. So I personally think that most acidic will be third. So most acidic will be third because it is having a negative M effect here. It's stabilizing the phenoxide ion. Then next should be, I guess, first, because at least it is having minus I effect and not plus M. Then first, then second or third, either any of them can come. So third, first is there, then I think second should come, because this is the worst, because it is showing you positive M effect drastically and making the molecule or the ion, phenoxide ion, more unstable. This is the order of acidic strength. Is it clear to all of you? So we have completed the first part, physical properties of acidity. Now we'll come to the second part, reactions of phenol. Acidity part is covered. Now we have reactions of phenol. We have first atmospheric oxidation reaction. So phenol under oxidation in the presence of either chromic acid, chromic oxide CrO3, or sometimes with air, it converts into para-benzoquinone and elimination of water take place. So H2 and this quinone will be formed like this. So simply just learn this reaction and move forward. Similarly, guys, when we react a phenol with K2S2O8, which is potassium persulfate, S2O8, and a mixture of catechol and quinol will be formed. So it's another important reaction, just directly learn it. No need to undergo for the mechanism is not required in this particular reaction. What noise is going on? Anyways, here is the next question, that on addition of hydrogen, it can lead you to the formation of either of the compound, whether it can lead you to the formation of cyclohexanone or cyclohexanol. This hydrogenation takes place in the presence of some metallic catalysts such as nickel, platinum, palladium, and can lead you to formation of these compounds. We have another very important reaction, everyone, very important. Why am I calling it very important? Because this reaction will be highly useful in conversions or like any of the middle of the steps of the reaction. So phenol on treating with zinc and on heating produces simply benzene and zinc oxide. Benzene and zinc oxide is the product. We have another reaction now, bromination reaction, and now we have entered to electrophilic aromatic substitution reactions. So there we all know that on on ortho and para, negative charge was there. So that is why ortho-para positions are highly active for electrophilic aromatic substitution reaction. Hydrogen belonging to that will be eliminated out. So let us say we are simply reacting it in Br2 in CS2. So guys, the reaction simply takes place that bromine nation will happen, then one bromine will eliminate it out as a positive form and as Br minus, and then Br will be attached here. So this reaction is actually happening on both of the positions clearly. Minor and major product will be these. And why is it minor? Because of the steric hindrance. Because of the steric hindrance of two groups which are near to each other. That's why this is becoming in a bit lesser yield. And this will go in higher yield. No steric hindrances here. So we have to learn this part, which is very important. That Br2 in non-polar medium. See, this is non-polar medium or like low polarity medium such as CHCl3 or CS2 carbon disulfide. Carbon disulfide is non-polar. It gives you mono substituted product, mono bromo product. But if you use water or a polar medium, we all know that OH group is highly activating group, and that makes you converting all the negative charge positions into the electrophilic aromatic substitution reaction. So like wherever you can find ortho and para position, they all will be converted down into 2,4,6 product will be there. So whenever phenol is treated with bromine in high polarity solvent such as water, it will give you 2,4,6 tribromophenol, which is also a confirmatory test of phenol. So phenol on treating with this 3Br2 in presence of water as medium, water, it will give you 2,4,6 triphenyl, and it's a white colored PPT which will be settled down. 3HBr will also for this is a laboratory test for presence of phenolic group. No doubt this is highly enough for your boards, mains, advanced, whatever you're preparing. Right after this, if you can do a proper practicing over this topic or chapter, it will give you solid basically help in your coming exams. So now I will take you to one of the another important reactions of bromination. This is how bromination is conducted. The mechanism is given. But since we already have covered this part under electrophilic aromatic substitution reactions of benzene, and then also in the terms of electrophilic aromatic substitution of the arenes, arenes as in haloarenes. So we already know this reaction. As I told you, this double bond will attack, one bromine will be there. This kind of compound will form cyclic halonium ion, and then this is something not required to do. Directly you can go from this to this. Hydrogen will be eliminated out, maintaining the aromaticity of the compound. These are singly substituted product. We also have multiple substituted product. Then we have nitration, guys. Nitration. So nitration is usually taking place under concentrated HNO3, concentrated H2SO4, and ortho and para positions will be acquired by nitro. But the problem over here is, see, when dilute nitric acid at low temperature is used, it yields to single substituted products of ortho and nitro. Dilute which we are using, cold conditions which we are using. But if you are heating this mixture or using a concentrated HNO3 where multiple NO2 positive groups are provided, electrophiles, they will go under the same reaction. 2,4,6 will be product. 2,4,6 trinitrophenol is called as picric acid. That will be our yield. Check it out, this reaction. Nitration of phenol. Now what is going on? Ortho and para can be separated by steam distillation. How do we use the steam distillation? Nitration of phenol. We have orthonitrophenol which is doing the intramolecular H bonding. It has low boiling point because of the intramolecular H bonding. It is not getting attached to the further other molecules. This, because of the intermolecular H bonding, can be attached to other molecules also. it is high boiling point and less volatility. And steam distillation process is something that can be utilized to separate these two mixtures, these two liquids. Nitration is also taking place in concentrated nitric acid, and I told you 2,4,6 trinitrophenol is formed. Guys, let me re-explain this part to you, that OH group present over the benzene ring is very activating in nature, and it can, even in the polar conditions or in the presence of water there as a high polar solvent, it can directly attack over ortho and para, all the ortho para positions, because OH group is highly activating group. But this can be reduced down and monosubstituted product can be produced using either cold conditions, dilute HNO3, or using non-polar medium CS2, CaCl3 as such medium for bromination we studied. But if you use a polar solvent, water, or you are using a concentrated acid or hot thing, this will yield to the preparation of 2,4,6 product, which is 2,4,6 trinitrophenol, called as picric acid. This compound is called as picric acid. Okay, the mole concept notes have not been shared with you till date. Anyways, we'll provide it. Thank you, Hritika. Hari, thank you. I'll provide it. Don't worry. Today itself it will be done. Now we have nitrosation. Nitrosation is what here? We have nitroso group, guys. So like HNO2, earlier I was treating it with HNO3 and nitro group, NO2 positive group was there, now NO positive is group was there. So we are supposed to produce the NO positive as an electrophile, and this is produced using by using HNO2 acid. So HNO2 acid on reaction with this produces an electrophile NO positive, gets attached to the ortho and para. Para is more stable. Its tautomerize formed is actually enol and called as quinone monoxime. Oxime group is N double bond. Carbon double bond N with OH group is called as oxime. So this is called as nitroso-oxime tautomerism. Nitroso-oxime tautomerism. Absolutely not a big deal, something that we have already studied. We have sulfonation, guys. Sulfonation is done under concentrated H2SO4, fuming H2SO4, or directly introducing SO3 gas. So SO3 is the electrophile that works here, and ortho and para positions will be acquired by sulfo groups SO3H. Sulfo groups are very big in size, and that's why it's not getting with ortho and para positions are not being occupied. Only ortho and para separately are occupied, and they all depends upon what temperature are we using. On higher temperature, it gives you para substituted product. On lesser temperature, it gives you ortho substituted. They also have intramolecular bonding with them. So this is how the reaction is working. We get SO3 as an electrophile. Then we have formation of picric acid by sulfonation, one of the another important reaction. We already have sulfonic acid with us, and sulfonic acid on reaction with concentrated HNO3 reaction gives you a picric acid. How? Let us study. A mixture of ortho and para nitrophenol on further heating with concentrated HNO3 forms a picric acid. During this reaction, nitration with simultaneous replacement of the sulfonic acid, this group by nitro occurs. So guys, as you all know, under the acidic conditions, sulfonation is a reversible process. We all know sulfonation is a reversible process, and sulfonation completed right after followed by adding acidic medium will lead you to the formation of either phenol, or here since we are using concentrated HNO3, it will convert it down into picric acid. I think this is important reaction and we should learn it. Now some of the good questions on the property just we studied. Ortho and para isomers of nitrophenol can be separated by steam distillation. Yes, they can be. True, because of the difference in the boiling point. One of them is more volatile, another one is a lesser volatile compound. Hello. So guys, try this question. हाँ भैया, किधर हैं आप? यस। अरे भैया, आप ऑर्डर लेके आए हो ना स्विगी से? नहीं, आप कहाँ पर हैं? Yes guys, now coming back to our question. So we have, हाँ भैया, So guys, please try this question, and right after this some of the practice session, we will be having our proper lunch break from here. 1 hour break, not 1 hour, 15 to 20 minute break. We have phenol with us attached with CS3. Br2H2O will produce two-side Br because one of the CS3 will not be replaced, and BrCS2 will give you mono substituted product. So I think A can be correct answer, right? Bi-substituted, single substituted. Why reaction with Br2 in front low polarity gives you, okay, fine here. As it is already explaining, it's a low polarity solvent. The reaction taking place is actually anti-addition of Br group, and electrophilic addition reaction takes place. Phenol reacts with Br2 in CS2 at low temperature to give you what? Phenol reacts with Br2 in CS2 to give you at low temperature gives you what? Phenol with Br2 at low temperature. I think ortho and para it will give you. Ortho and para. Monosubstituted. Phenol when first react with concentrated sulfuric acid, it will give you sulfonic acid, and then treated with nitric acid will give you 2,4,6 trinitrophenol. Yeah, remember this reaction, that phenol with concentrated H2SO4 gives you OH and then sulfonic acid. Ortho or para, which upon reaction with HNO3, and that also concentrated under the influence of phenol, which is a very activating group, it gives you 2,4,6 trinitrophenol, which is called as picric acid. Phenol with zinc dust, we all know it will give you benzene. Benzene on CH3 anhydrous Cl3, we call this reaction as Friedel-Crafts alkylation. Alkylation will take place. CH3 will be attached. Toluene is the product. Toluene under acidic conditions, alkaline KMnO4 as a strong oxidizing agent, all the hydrogen will become OH. It will be converted to COH. Correct answer, benzoic acid. Phenol gives benzene while heated with Y. What is this? Zinc dust? Simply. Soda lime, no, not like that. Soda lime doesn't give you any reaction because it is used only for the decarboxylations of carboxylic acid salts. So guys, there we have completed one of the part, very important part from here. Now I will take a bit break, and this is what are remaining along with ethers. So now let me announce a break. So we are now having a lunch break. So those who have not liked the session, do like the session. And we'll connect back, so just stay tuned. So that was some healthy break we had. Hopefully you all have done with your lunch. I'll resume the lecture from here. First of all, let us know where were we and till where we just completed. Okay, so we were about to start it from here. We have some reactions of phenol part 1. We have reactions of phenol part 2. Part 1, part 2 are actually, these are some mixed and some naming reactions and highly important reactions. Also, these reactions are kind of miscellaneous reactions which are now left behind. We will cover these 6 reactions for phenol. We also will study about the bakelite formation and the uses of alcohol and phenol, and then we'll come to the final part of this chapter, ethers. Not working. There we have first reaction. Guys, this reaction is known as Fries rearrangement. What happens in the terms of Fries rearrangement? This reaction happens in presence of the non-polar or weakly polar solvent, and where AlCl3 anhydrous AlCl3 is used as a catalyst. So I'll explain how this reaction works. First of all, let us know that this reaction happens in the case of ester. This is your phenyl ester. We call it like alkyl alkanoate. So this is your phenyl and metheth ethanoate. So this is your phenyl ester. It, under the presence of AlCl3 and anhydrous HCl, undergoes some rearrangement reaction and forming this group. This group is attached ortho and para positions respectively, forming ortho. What do we call it? Acetyl group is there, no? Ortho acetophenol or para acetophenol. That is what the name of this compound. Now let us check out the mechanism, very easy mechanism. So initially we are having this compound over here, and due to which this a complete proportion is formed here. This forms a complex like this, and this group RC double bond O, this group with a positive charge, this group with a positive charge works as an electrophile. Now this electrophile attacks upon the benzene rings so formed, ortho and para positions are available, and this respective compound is formed. And in the presence of water or like acidic medium, that it can again be converted back into OH group, and AlOH Cl4- will be your further compound. So we have Gattermann formylation reaction from here. Gattermann formylation reaction is one of the similar reaction in which electrophilic aromatic substitution will occur. How? Let us check it out. So guys, HCl plus H, this HCN will actually react with HCl and will give you a carbocation here. It's working as an electrophile. This will become NH. Let me check it out. What is it? Does it make? It is H plus. So H carbon Cl double bond NH. This is how it is formed. This compound in presence of AlCl3 will give you HC double bond NH positive as an electrophile. This is an electrophile, plus AlCl4- will be formed. This electrophile now attacks upon ortho and para position. So guys, how can we go? Let us suppose this is benzene, phenol, and we have this compound Hc positive double bond NH as an electrophile attacking, so it will give you OH, and we will be having C double bond NH, and then we have H, and one more compound will be there at para position, same CH double bond NH, and here is OH. In our next step, what we will do, we will hydrolyzing this H2O, and this gets converted into NH3 will be eliminated out. This will be converted into C double bond of H, CHO, and this will be converted into. So since we are adding a formyl group, or we can say we are adding a aldehydic group, this reaction is called as Gaterman formylation reaction. So always remember what are the reagent which we are using. Where the reagents are HCN plus HCl plus anhydrous AlCl3, and that produces what? An electrophile, this. Hopefully this part is absolutely clear to all of you. Very interesting and very important naming reaction called as Reimer-Tiemann reaction. Reimer-Tiemann reaction. So what is Reimer-Tiemann reaction? So guys, in presence of CHCl3 in aqueous NaOH, this produces a reaction intermediate called as CCl2 dichlorocarbene. This dichlorocarbene reacts as an attacks on benzene as an electrophile. This is how it is substituted, and CCl2 with a negative charge, then it acquires H from the water. It becomes this kind of intermediate. This intermediate later on the attack of NaOH can converted into CHO like on hydrolysis. So that's how the reaction works, and it gives you salicylaldehyde. Salicylaldehyde is what? Ortho and para substituted CHO group of phenol. That is a salicylaldehyde. An application of electrophilic aromatic substitution reaction. Won't take too much of our time. Let's move forward. We have similar type of reaction called as Kolbe's reaction. Not what is this here? No. Reimer-Tiemann in the presence of CCl4, if we are using, then it gives you CCl3. In the place of CHCl3, if we use it CCl4, then guys the CCl3 positive, let's say, is the electrophile produced, and this electrophile will be substituted by OH groups at once, and then salicylaldehyde will be, salicylic acid will be the major product. And why is it the major product? Because of the intramolecular H bonding. Because of the formation of intramolecular H bonding, major product will be this. However, more stable product is always the para one. We have mechanism here which we do not need because we already have explained this part. First step, the reaction of chloroform with NaOH leads to the formation of CCl3 negative. CCl3 negative, Cl minus departs, forming CCl2 intermediate called as dichlorocarbene. Carbene works as an electrophile. On electrophile, carbon attacks, giving a negative charge to CCl2 negative. This negative charge acquires a positive charge from here, forms a compound like this, and then di substitution occurs. Di substitution is in 2Cl negative, 2Cl are replaced by 2OH in the basic medium, and it produces finally this compound. On acidic treatment, this gives you salicylaldehyde. Not a big problem, not a big reaction mechanism. It's easy, and those whoever are preparing for their boards, this reaction can be sometimes asked in your boards exam also of 12th standard. So do make proper notes out of it and learn them. Next one, pyrrole also gives you the same reaction, but there are like some abnormal products also. Now what is the meaning of this abnormal product? I'll let you know. Allow me a moment. I'm just checking out how much is left, by the way, from here. We have Kolbe's reaction, we have this is zup. No problem. So pyrrole also undergoes the similar kind of reaction, but in pyrrole, who will attack? And ortho and pair positions are these. This is how it will form a C2. It also forms another compound called as this. So that is an abnormal product which you are getting. This is the simply product which you are expecting. This is the abnormal product. So let us see how does this abnormal product comes up. Initially, it is OH is reacting with CH3 chloroform, giving you CCl2 dichlorocarbene as an electrophile. On this electrophile, this given compound pyrrole attacks, and pyrrole attacks in two ways. The very one of them is nitrogen is attacking. So one is first of all, let us go for the normal product. Nitrogen. So dichlorocarbene it is attacking, and then this dichlorocarbene removes hydrogen, and CHCl2 will form. Okay, this is the similar reaction only, not so different. Let us see the abnormal product, how it is forming. This is how the abnormal product is forming. Rearrangement takes place. Negative charge comes here. This come here, and this leaves. Okay, fine. Then this is an abnormal product. So this case happens only in terms of pyrrole, doesn't happen in the terms of benzene or phenol, and that's why in phenol only one product is formed. But anyways, this reaction is given and we have studied it. Not given in CRT, not required too much, but just take an idea that what kind of compound it's like meta substituted pyridine. It's pyridine, which you can see nitrogen and this benzene looking substance, aromatic, and with Cl at the position will come up. So phenyl esters on treatment with anhydrous AlCl3 with the CS2. Fry's rearrangement? Yes, absolutely. What is Fry rearrangement? Let me tell you. Sir, what is the meaning of phenyl? Sir, this should be connected with O. C double bond O R. This is called as phenyl ester. Phenyl alkanoate. Then under AlCl3, heat gives you two products, one ortho substituted, another one is para substituted. This is your ortho, and this one is para substituted product, like that. The true. Another reaction. So we have this reaction. This will give you the formation of CCl3 minus Na plus water, out of which Cl minus eliminates out, forming CCl2 dichlorocarbene as an intermediate. So dichlorocarbene, D is the correct answer. Reimer-Tiemann reaction. Where is the Reimer-Tiemann reaction, guys? You do it by your own. Yeah, simple reaction. CaCl3 is the correct answer. By which process phenyl acetate can be converted? Fry's. Reaction of phenol with chloroform. HCN, this is Gaterman formylation. Next comes is Kolbe's reaction. What is Kolbe's reaction? Kolbe's reaction is exactly the similar reaction, only the reagents are a bit different. Initially we are using NaOH followed by CO2 and acidic medium. So let's see how does this reaction go. Oh my god, not given, no problem, I'll make it. Initially we are using NaOH. Why? Because CO2 being a weak electrophile doesn't get easily attacked. Let us first make O minus Na plus. Now it is highly activating. Now since it is highly activating, this will create a negative charge, and this attacks upon C double bond O double bond O. This attacks on the carbonyl carbon. Electron density moves like this. So preparation of a compound like O minus Na plus. About O minus, simply just type double bond O. It is simply here, it is simply here. We have C double bond O O minus here, and one hydrogen is also here. So in the next step, this hydrogen departs, forming it as O minus. And this will become what? OH. And here will be CO negative. So if we treat this reaction with dilute HCl, or let us say any of the acidic medium is there, this gets converted into. So since I made here ortho, you can also make para. This is called as ortho salicylic acid. Salicylic acid, not cyclic, it's salicylic acid. And what is O? Ortho salicylic acid. Similarly, you can make para salicylic acid also. So guys, you can see the applications of salicylic acids are as given. This is an important reaction, an important compound, by the way. There happens a SN2TH reaction. This group remains as it is. So first reaction, let us suppose this is working and attacking there and removing this portion, then it will become COH as it is, OCOCH3. So it's like acetar also is here, a carbonylic acid is also here. We call it like acetyl group. So orthoacetyl salicylic acid, this is called as aspirin. O-acetyl salicylic acid. Aspirin is called. One of the important reagent in medicinal purpose, aspirin. Another reaction is esterification. This OH group and this removes the water molecule and then forms the ester. So this is methyl salicylate, also called as the oil of wintergreen. Nice here, oil of wintergreen. And then the reaction with phenol will also give the similar kind of compound called as salol, phenyl salicylate, salol. Exactly the similar kind of ester will be formed. I don't think it's too much to basically remind you about. Similar kind of reactions have been already completed by us. I'll move forward so that we can reach to the further milestone. Now some questions. The reaction of sodium phenoxide with carbon dioxide at high temperature gives you what? For a salicylic acid, correct? True. What is the product? Tell me. So guys, this is how it will attack. Attacking here, it will come down here. Cl is the leaving group, departs. The correct product will be, this reaction is called as what? SN2TH. I'll explain this reaction when I'll be teaching you Grignard reagent, because all the acid derivatives with Grignard shows this kind of reaction. So this is how it will be formed. OC double bond O, CH3 and COH. So we call it orthoacetyl salicylate. So the correct answer is orthoacetyl salicylate. O-acetyl. It's not ortho, it's complete O-acetyl salicylate. Salicylic acid, sorry. We have a coupling reaction. Coupling reaction will be very much useful, and that reaction will also come in amines, in the chemical properties of amines, especially in diazotization reaction. So diazotization is pretty simple to all of us. We need an aniline. We react it with nitrous acid HNO2, which can be prepared freshly by HCl and NO2, and right after that reaction under low temperature we prepare a benzene diazonium chloride like this. On reaction of this compound with phenol, it gives you a para bonded a kind of reaction. So this N2 plus will be attack over here, and this is how as an electrophile, this working as an electrophile, electrophilic aromatic substitution will take place. This is the product forming. Para hydroxy azobenzene. Okay, this is azobenzene, this is para hydroxy azobenzene, called as orange color dye. It's orange color dye. And next reaction is phthalic anhydride. So what is phthalic anhydride, everyone? A reaction with phthalic anhydride produces PHP, which is called as phenolphthalein. We also have an important compound called as phenolphthalein produced by this reaction. I'm trying to stretch myself here. So this reaction is actually This compound is called as phenolphthalein. Phenolphthalein. So how is it formed? Represented by PHP. The reaction of phthalic anhydride. This is called as phthalic anhydride, and it is prepared by phthalic acid, dehydration of phthalic acid. This is become phthalic anhydride, and similarly SN2TH reaction will take place. Not here. So let us suppose from here. This is how the reaction will take place. Simply learn this reaction that it has like two bonds with oxygen. Both of them will be substituted, and it will be forming C-double bond on. This another one will be attached with two phenol group. It becomes phenolphthalein. It's an important reaction. This reaction was asked in JEE Advanced 2020. For this question, similar question was asked. Next, we have one question here, everyone. So, what is the X here? So, X should be NaOH so that it can increase the electrophilicity of this reaction, and once this converted into O minus, then it has become more electron rich. Correct answer should be NaOH. Coupling reaction carried out in basic medium. True. To increase electron density of benzene ring. Why coupling reaction carried out? Okay, we done here. Para, because para product will be more stable. Sterically, it's very crowded. So para product will be more stable. Then product of Kolbe's reaction. Kolbe's reaction will give you salicylic acid, simply, ortho and para. Salicylic acid is on X and Y will zoop, 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 zoop. So this product has to be formed. I'll make this product for you. Number one. O C-double CH3. So I will use CH3 COOCl first, and second we can use pyridine. Why we are using pyridine? Because HCl is the byproduct. And it can be neutralized because in acidic medium it can convert back into acid and alcohol. It is neutralized by byproduct, is neutralized by pyridine, which is nothing but a weak base. So correct answer should be both A and B. Very simple reaction. What is this? This is phenolphthalein, PHP. We have next reaction called as bakelite formation. We also call it reaction as bakelite resin or phenol formaldehyde resin. So let's move forward then. So we have one reaction, guys. I would like to suggest you, I mean, as of now, since we all know polymer is not in our syllabus, there is a chapter, separate chapter by the name of polymer, not in our syllabus as of now in mains. We'll simply take an idea and then we'll move forward, and later on we'll try to cover that part also. So guys, how does this reaction take place? We are initially getting this compound which is HC double bond O H. So getting this compound reacted with acidic or basic medium, either way is fine. So ये this kind of electrophile is there. Now this electrophile will be attacked on ortho and para position, forming these compounds CH2OH, CH2OH, and another CH2OH will be there, and this water is eliminated out. And not just water, it is completely eliminated out, forming carbon-carbon bonds. The mechanism is a bit different, but just take this idea that it is connected with CH2 group. The single line linear polymer is called as Novolac, one of the alternative of rubber used in paints. So Novolac, on heating with formaldehyde, goes for cross-linking, forming an infusible compound called as bakelite. Now it is forming a thermosetting polymer. This is the thermosetting polymer look like, and so on. This carried out in all the directions, but this is called as bakelite. Then some important alcohol and their uses. We have methanol. Guys, methanol, the chemical formula is CH3OH. The uses are, it is also called as wood spirit, and since it's originated by wood, destructive distillation of wood, that's why we call it. And nowadays it is prepared by catalytic hydrogenation of water gas. Water gas is Cu plus H2 under CuOZn or CrO3. Under high temperature it produces CH3OH. Uses: largely used in paints, varnishes, celluloids. It is used in the manufacture of formaldehyde, also used in denaturizing the alcohol. Denaturation is a process in which ethyl alcohol, which is actually a drinkable alcohol, is mixed with ethanol in order to make it poisonous. Because in laboratories, what scientists do, if they have pure ethanol, they can add some water in it and can drink it and can enjoy, but that enjoyment is stopped by mixing some poison in it, which is methanol, and then nobody is supposed to drink it. And denatured alcohol is also called as methylated spirit. Then we have in manufacturing of very perfumes, it's not performs, it is perfumes and drugs. Then we have ethanol. Ethanol is actually prepared by hydration of ethene. And hydration ethene is one of the way. Formation of carbohydrate gives only 95% alcohol. Ethanol is mainly prepared by hydration of ethene. Fine. Formation of carbohydrate is what, yeah? And it only gives you 95% of alcohol, rest being water, and this is called as rectified spirit. Okay, it is used in antiseptics, solvent, as paints, lacquers, and varnishing, dyes, cosmetic, perfume, tincture, cough syrup, etc. And as an important starting material, this can be used in formation of the ether, chloroform, iodoform, etc. It is important in beverages, so alcoholic beverages such as beer, wine, vodka, etc. can be prepared. And then we have power alcohol is a mixture of 20% absolute alcohol, pure alcohol, and 80% petrol, and then it is used as a gasoline with benzene and toluene as a co-solvent. Okay, so used with power alcohol only, so power fuel. Also used in antifreeze in mobile radiator. And absolute alcohol is alcohol with 100% ethanol prepared by rectified spirit as follows. In laboratory, actually 95.5% spirit, it comes into contact with calculated amount of quick lime in few hours, the reflexing and distillation. So somewhere we are using quick lime CaO in order to remove the water in terms of CaOH whole twice, and remaining will be the 100% alcohol called as absolute alcohol. Third is phenol or carbolic acid. We'll understand and we'll study the uses of this compound. This can be used as an antiseptic and disinfectant in soap and lotions, also used in drug like aspirin, Celol, Xylia. The moment back only we studied it. It is also used in preparation of bakelite, and it is in the manufacturing picric acid, phenolphthalein, azodyes, preservatives of ink, etc. That's it. So these are the questions which you will do by your own hand. No man, I don't have any time for that. Finally, we have come to the final part of this chapter. That is none other than introduction to ether. Introduction to ether. Guys, this is called as ether. ROR, if these are the same, called as symmetric ether. Symmetric ether or simple ether. And if R and R dash are there, some another alkyl group is there, it's called as unsymmetric. Oblique mixed ether. See? So now, let us take their introductory part. So mixed and unsymmetric is already known. Then nomenclature. So guys, commonly we call them alkyl ether, alkyl ether, like dimethyl ether, diethyl ether. If ethyl and methyl is there, alphabetically we'll go for E. E alphabetically, E and M. We have to go alphabetically. IUPAC it is pretty much simple. Take the smaller part here, one carbon chain, methoxymethane. Then 1 and 2, ethoxyethane. Like this is methoxy 1, 2. So 1 methoxyethane. Very simple. Introductory part is here. So we have this structure. No doubt this oxygen is sp2 hybridized. Sorry yaar, sp2 nahi, sp3 hybridized. 2 lone pairs, 2 bond pairs. So their physical property, if we talk about, their with the size, their boiling point increases, and they have higher than alkanes but lesser than alcohols, because alcohols have H bonding between them. They do not have H bonding, but they have polar molecules have dipole-dipole interaction. So that's why their boiling point is higher than, undoubtedly higher than alkanes, but not beyond alcohols. Alcohols, they are lesser than alcohols, more than alkanes. These are very much self-explanatory notes. I would expect you people to please revise these notes as quick as possible right after the class, and I'm moving forward. Then we have ethers exhibit type of structural isomerism. Functional isomerism they also possess, because functional isomerism of alcohols. Here are some examples. Next is isomerism. Metamerism is also shown. Metamerism is different presence of different groups beside of this polyvalent functional group. The groups must be different. See, and there also. Chain isomerism can also be shown by ethers. Chain isomerism. Let's see how. So this could be 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4, 5. That's one example. I'm trying to make chain. Chain means you have to make different chains for this. So the 1 2 3 4 5. Then how many carbon atoms? 1 2 3 are there? Any other possibility, Sanjay? I think these two are the perfect examples. Now it will become positional. Not a problem. Then we have physical properties. Guys, they have low boiling point because of their less polarity, and they have low solubility in water because of lesser extent of H bonding with water, which was exactly higher, which was seen higher in the terms of alcohol and carboxylic acid. That's why I have the highest boiling points, because they have a higher extent of H bonding. We have some of the basic questions here. Solubility of ether in water decreases with increase in molar. Correct, true, because the hydrophobic part will increase and that will keep an ether undissolved. Why ROR bond angle in ether is larger than 110 degree? What do you think? Why? Oh my god, why is it large here? That we have to check. I thought it will be lesser than that. Here it is. And it is 111. So bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between two bulky alkyl group. Okay, because of the bulky alkyl group and smaller size of oxygen, because smaller size of oxygen is also there. So hopefully this part now is totally covered and completely explainable. That's our O, R and R. So these bulky groups cause repulsion, due to which this bond angle theta reaches to 111 degree. IUPAC name of this compound. So see, wherever you find a smaller group is there, you make that group as a substituent. This will become a substituent. Name 1, 2, 3. So we have 2-methyl and this is ethoxy. So ethoxy will come first. 2-ethoxy, 2-methyl methylpropane. D is the correct answer. See how easy is this. Another question. Which one among the following is least soluble in water, is very less soluble in water? What do you think? Which one is the less soluble in water? So it is ethanol, propanol, whatever it is bigger in size. So ethoxyethane, I guess, is the correct answer, because C2H5 O C2H5, bigger is the alkyl part, less is the solubility, and alcohols are always more soluble than ethers. That is why correct answer is D, bigger ether, big size ether. So with this, now we have reached to another milestone of this chapter, which is the preparation of ether. So how we prepare ether, and then after ether we'll be understanding their physical properties are covered, so we'll understand their chemical properties, only chemical reactions. So Williamson synthesis is the best method. Let me write it, is the best method. So guys, how we do it, let me tell you. We initially have an alcohol. Ether has to be made, no? We have to react it with NaOH it will give you ROH, RO minus Na plus. This has become a nucleophile now. Now there is a compound called as R dash Cl, or let us say X alkyl halide. So on which we are attacking with this R dash O minus. And this attack takes place in one step. This is SN2. So what will be the product? RO R dash. What is RO R dash? This is ether. So this is very best method to synthesize symmetric, unsymmetric, whatever be the nature of ether is there. This method is useful for all the cases of synthesis of ether. This is called as Williamson synthesis method. Now we'll come to some of the example. So guys, I want to give you one important example here, and I want to like to tell you that what you can't prepare and what you can prepare. So let us say that we have this possibility with us. We have two things. So the outcome, final outcome is, let's say this OCS3. We have to make this compound. We call this compound as anisole. Anisole, sure, anisole. Fine. So there are two ways. Now you have to tell me which one of the way is correct. So one way is Cl, and then we are attacking it with CH3O minus Na plus. The another method could be, we have मैं लिखूं तू आ जाए, मैं बैठ लिखूं तू आ बैठे. So guys, now you tell me which one of them is correct. This is like path 1. This is path 2. One of them is correct, another one is not. So guys, this attacking over here, ARSN, which is like not possible. So this is impossible, and this is possible. Why? Because this can easily undergo this, which is like SN2. SN2 is possible. So do remember these things, that benzene attached with an halogen neither undergoes SN1 easily nor goes SN2, but SN2 can be very easy if CH3Cl is the substrate. Attacking reagent will be phenoxide ion. So preparation of mixed ether by Williamson synthesis. Alkyl halide should be primary. As I told you, this reaction is SN2. It follows 1 degree, 2 degree and 3 degree. 3 degree give elimination. So basically alkene as product is born. The product will be alkene, not ethers. That's why we don't use 3 degree. Another important reaction or preparation method of ether is the dehydration of alcohol. So guys, dehydration of alcohol is another simply reaction which is exactly happening like dehydration of alcohol was earlier producing elimination reaction and the product was an alkene. Now substitution will occur at low temperatures. So this is how the reaction will work. And this is acid catalyzed dehydration of 1 degree is a SN2 reaction. 2 degree and 3 degree it follows what? SN1 reaction with the formation of carbonyls. See, step 1, hydration is taking place, protonation is taking place, protonated alcohol is formed. Protonated alcohol may remove itself in the form of 2 degree to 3 degree. Carbocation will be formed and then attacks another alcohol and forming and this kind of ion. After removal of H plus, it will give you ethoxyethane. Any kind of ether can be made. But secondary and tertiary, they easily undergo, in terms of especially 3 degree or 2 degree, SN1 reaction takes place, but some of the products will be elimination also. Another reaction is alkoxymercuration and demercuration. So guys, earlier we were using mercuric acetate. Here they are using exactly mercuric acetate only, but only instead of hydrogen there is fluorine, but not a problem. This compound is also doing the same reaction and will produce the required desired product. Alkoxymercuration, demercuration. So please look at the examples, everyone. I'm feeling a bit exhausted, so you better carry on with these examples. Somebody has come back, texted me. Okay, thank you, Dipankar, for your best wishes. Dipankar, please focus on this. Whatever you're writing is not going to come in your exam. This will come in your exam. Be focused on that. We have a simple reaction of alkene. Alkene, first of all, we are doing mercuric attack with mercuric acetate or like trifluoromercuric acetate. And then we are having ROH instead of HOH. So initially H and OH will be attacked there. Now H and OR will be attacking. Very similar reaction. So whenever any question will come, I'll help you. We also have one more reaction that heating with dry oxide, dry silver oxide will give you this. So guys, remember this reaction that Rx in presence of dry Ag2O produces ROR, and if we are using wet or oblique moist Ag2O, the product will become ROH. Alcohol is the product. We have another important reaction, action of diazomethane on alcohol, that ROH on reaction with CH2N2 and in presence of BF3 produces ROCH3. Okay, good. This reaction is pretty easy. In this reaction, by the way, the ROH is attacking here and N2 will be departed as nitrogen, and that's it. The hydrogen will be taken by CH2 group only, CH2 minus. This will become CH3. Which of the following reaction the product obtained is tertiary butyl methyl ether? Tertiary butyl is this. So guys, I gave you the similar example once back, that this CH3Cl can undergo SN2 reaction. CH3Br, this is correct because this is undergoing SN2 reaction. So this will come, attack here and can remove this. But why is it not suitable for this? This will give you elimination reaction, E2 reaction. It's a base. This will attack on this. hydrogen will come and this will depart. CH3, C, double bond CH2, CH3. Alkene will be the product. Not correct. We have a question here. Methyl propane 2-ol. Okay, first of all, let us make it methyl propane 2-ol. 1, 2, 3. 2 methyl and propane 2-ol. Actually, this is tertiary butanol. So if tertiary butanol is there and we are reacting it with like in acidic medium, so H plus will take let's say H2 is departed, so this will form what? Now there could be two possibilities. If CH3, another equivalent if attacks here, there could be two possibilities. One which is called as SN1 and the another could be called as E1. Both of them can happen. The correct product will be CH3C, CH3, CH3, O, C, CH3, CH3, CH3. One product is this and the another product will be elimination product CH3, C, double bond CH2, single bond CH3. So both of the products will be formed here. And all depends upon the temperature condition. Higher temperature gives you elimination product, lower temperature gives you, and here also specifically more product will be because of alkene. So that's why this is not a very suitable reaction to synthesize the ethers, and that's why we prefer the previous reaction only. The name was Williamson synthesis reaction. Rest of the question will be done by you. This is the homework. And now cyclic ethers, we also call them epoxides. Yes, so what is epoxies now? Let us discuss about epoxy, guys, one by one. There are two methods of preparation of epoxies. One is insertion mechanism, and that was proposed by peroxy acid. That it could be any peroxy acid. It could be H2SO5 also. It could be CH3COOH. Instead of that, so use CH3COOH. Nahi yaar, CH3COOH 3 times. So metachloroperbenzoic acid or CH3C triple OH, these are the same function. They will introduce one oxygen group between two doubly bonded carbon atom. So this is how epoxy will be formed. Just simply learn. There is no need to write down their mechanism. I have already explained you mechanism in the start of the reaction, in the start of this chapter. So simply learn. In the preparation of alcohol, I gave you this example because once these compound will be attacked by in acidic medium or in basic medium, the alcohol will be formed as a product. One reaction. Another reaction is base catalyze beta halo alcohol is there. Now what does that mean? Actually the meaning is pretty simple. Beta halo, let us suppose here beta halogen, alpha is hydroxy here. So in the first reaction, one hydrogen in the base, hydrogen will be detected, like removed, O minus becomes a nucleophile then, and then internally SN I reaction will be done. Intramolecular will attack, this will remove. Like that the reaction takes place. So it's instead of so these are very easy reactions. Beta halo alcohols also give you the similar reaction. Let us take you to some example. We have ring opening reactions. We have some set of reactions for cyclic ethers and all. So guys, I will explain this part as I promised you earlier of the class that SN1 type and SN2 type, there are two type of reactions. Let me explain that part to you. Let us suppose we have, here I'm explaining you SN1 type ring opening of epoxides. So first of all, you must know that this reaction occurs in acidic medium. This reaction will be occurring in acidic medium whenever H plus is given or H2 is attacking or whatever it is happening, but everything is in acid medium. How acid reaction looks? See, let us suppose this is one epoxy. This is one epoxy. Now this epoxy has been attacked by, let us suppose, water or H3O plus. Try to understand it. Acidic medium is there, or H plus is there. So in the very first part, this O will be attached by one hydrogen, and this positive charge is actually surrounded on all the atoms. All the atoms, like 3 atoms are there. So this is like this is how it represented by like this, like this, like this, and the positive charge is like partial positive, partial positive, partial positive. Everywhere is the partial positive charge. Everywhere, equally distributed. So now, since it is equally distributed, it will reside more onto that carbon which is like more crowded, which will can give it more extra plus I effect. So in the next step, let us suppose any nucleophile comes, or any, let's say, water molecule already comes and wants to attack. So this will prefer this way. This way will be preferred rather than following this. This way will not be preferred. Why? Because this is what we are calling it SN1 type. Because there is no pure carbocation formed. There is a cyclic oxonium ation is there on which water will attack. Let us see the final product. Guys, this is how it looked like. Attack is happening on this carbon. Let us suppose anti basically will be there. Anti-periplanar OH group will be there, because let's say the attack is taking from this side. This will be the ring opening. Then it will be like OH here. This is already there, but these two are anti to each other. So that is how the final product is formed. And that's why we said ring. This is called as SN1 type, because more crowded carbon atom will be getting attacked, because there we have more stable cation is there. Now in basic medium, what happens if we are having the basic medium, or let us suppose the attacking reagent is itself is a base, or it more or less like a Grignard reagent, nucleophilic directly attack. This follows SN2 type ring opening ceremony. So what will happen here? See, we are using the same compound, and let's suppose initially only R-MgX is used. R-MgX is used, which is, why am I using R dash? So guys, this nucleophile will attack directly onto less crowded, less hindered carbon atom. What will it make? And the similar way, this will be leaving down. This will become O negative. Attack is happening on the opposite sides. So this will look like this. At last, what you will do? At last, hydrolysis can be done in acidic medium, but again, this reaction has followed what? Similarly, very simply, this has followed what? SN2 type attack. SN2, why am I calling it type? Because this is your final product. Please learn this whole and try to balance between these two, and also learn where you have to put what kind of reagent, what will be the final product, and I'll give you some reactions related to it. And since we already have completed 5 hours in this chapter, we'll be winding up this session in just coming 10 minutes. I will wind up this session in 10 minutes. Yeah, hi Nikhil Yadav. Very good Tejasvi, very nice of you. चल रहा एक ऐसी नज़्म कहूँ जो लफ्ज़ कहूँ वो जाए। मैं आ लिखूं तू आ जाए, मैं बैठ लिखूं तू बैठे, मेरे शाने पर सर रखे तू, मैं नींद कहूं तू सो जाए। चल आ एक ऐसी नज़्म कहूं, जो लफ्ज़ कहूं वो जाए। मैं दिल लिखूं तू दिल थामे, मैं गुम लिखूं हो जाए। Anyways, यार, where were we? हाँ, so this part is completed now. Reaction of cyclic ether we'll do, and then we'll wind up the session. We have this part which is completed. This is also completed. We will come to some of the questions and then we'll wind up the session. Okay, one more thing I wanted to explain over here is the addition of HI, which is not given here. So anyways, I will explain that part over here. Second very important reaction is addition of HI, or let's say HX. Okay guys, so what will be happening? See, let us suppose this is a cyclic ether. So let's say I'm putting HI here. So guys, always remember, if any oxygen connected carbon is 3 degree, then carbocation will be formed, right? Case 1. So what will be happening? First step, this will OH automatically this will break down this like this, and it will give you not oppositely, it will be done, so that a stable carbocation you can get like this. Then in the next step, this will be like O negative, sorry, not O negative, it will simply OH. In next step, then I minus will attack, and then I minus will attack here, and you will get your product like I here and OH here. So that's how we will make the product. Okay, case 1, if stable carbocation is formed, like benzylic allylic 3 degree, etc. If this is the case, then case 1 will be used, and this is how the product will be formed. There is one more possibility, case number 2. If 2 degree or 1 degree carbon is there, no carbocation is formed, and SN2 type reaction occurs. SN2 type reaction occurs. There was SN1 type earlier we were using, and let me write SN1 type. Here, let us suppose this is the compound given. So initially, no doubt H plus will come, and this will not break by itself. It will be remaining like this only. In the next step, I minus comes and then attacks like SN2 type. Where should it attack? On the more hindered or the less hindered? On the less hindered. And then ring opening takes place like this. So this is I, this is like OH, and this is your compound. This is the compound form. So try to understand these both cases, which are very similar to each other but entirely different also from each other. Now we'll solve some question and we'll get the clarity about the topic. So during cleavage of epoxy, nucleophilic attacks on the more substituted carbon. More substituted SN1 true. If it attacks on the more substituted carbon, then SN1 type. Okay, this is the compound, and we can see that this will be a 2 degree, not just 2 degree. It's simply 2 degree, and this is simply 1 degree. So where should I attack compound? And this will and this is simply like this. So next step, I minus will come and will attack on the least hindered one, and this reaction is SN2 type attack. SN2 type attack. So what will be the happening? What will be the product? We'll be getting OH into that direction. CH3 OH iodine. Can you see any product like this? CH3 OH and iodine. This is the correct answer. C. Please observe it. Ethylene oxide with Grignard. Grignard reagent. Ethylene oxide is what? So guys, since this is a what I can say normal, it's a symmetric kind of situation. So anywhere it can be attacked, anywhere like this, SN2 type reaction will occur. CH2, this will become O minus, MgX plus, and this is your CH2, and R is connected here, and then water will attack and will give you what? CH2, CH2, R, and this will give you OH. So it's a, what degree alcohol is there? It's a primary. So 1 degree alcohol. A is the correct answer. Why base opening SN2 that I have already explained? Then this is some homework for you. You do it by your own. This is some homework for you. Do it by your own. This is simply question SN2 type. And thank you. So that's it guys for the day. Okay, well, nice. Yeah, somebody was consistently watching. Thank you. Sleepy Mew.